Some parts of history were never meant to be fully explained. Throughout ancient history, archaeologists have uncovered cities, monuments, and artifacts that suggest a level of precision and planning difficult to fully understand. Massive structures rise in places where technology was assumed to be limited, while entire settlements appear with organization that hints at deeper systems of knowledge. These discoveries show that ancient societies were capable of shaping their world in ways that still challenge modern interpretation. Yet the ideas behind these achievements are rarely preserved. We can study the structures and analyze the materials, but the reasoning often remains unclear. These ancient mysteries suggest that the foundations of human civilization may be far more complex than we realize. A landscape that should never have supported civilization somehow became one of the most advanced agricultural systems ever built. High in the Andes Mountains, where oxygen is scarce, temperatures swing violently between day and night, and the terrain itself seems to resist human control. The engineers of the Inca civilization created something that modern science still struggles to fully explain. At first glance, the terraces carved into the mountainsides of Peru, especially those at Machu Picchu, appear to be simple farming platforms. But hidden within their geometry is a system that does far more than grow crops. It controls water, stabilizes mountains, and, most mysteriously, manipulates climate itself. The story of their rediscovery begins in 1911, when the Yale Peruvian expeditions brought global attention to Machu Picchu, revealing not just a lost city, but an entire engineered landscape. Early observers documented the terraces primarily as erosion control structures, designed to prevent landslides in a region where annual rainfall can exceed 1,000 millimeters. Yet even in these first reports, subtle anomalies emerged. The terraces were not randomly distributed. Their angles, spacing, and elevation shifts followed patterns too consistent to be explained by intuition alone. As archaeological surveys expanded across the Sacred Valley throughout the mid-20th century, researchers began to recognize that these were not isolated farming solutions, but components of a unified environmental system. That realization deepened dramatically with the investigation of Moray, a site unlike any other in the Andes. Rather than linear terraces hugging mountain slopes, Moray consists of enormous concentric circles carved directly into the earth, descending approximately 30 meters from rim to center. Initial interpretations range from ceremonial amphitheater to storage complex, but none adequately explained its precise geometry. It was only when systematic measurements began, particularly temperature recordings taken across different terrace levels, that the true nature of the site started to emerge. Researchers documented consistent thermal gradients of 10 to 15 degrees Celsius between the uppermost and lowest rings. In practical terms, this means that a single structure could replicate environmental conditions equivalent to multiple altitudinal zones across the Andes. This discovery transformed Moray from an archaeological curiosity into one of the most compelling examples of ancient environmental engineering ever identified. What stood before researchers was not merely a farming system, but a functioning microclimate laboratory, an ancient facility capable of simulating different ecological conditions within a controlled architectural space. Each descending level alters wind flow, sunlight exposure, humidity retention, and thermal behavior. The stone retaining walls act as thermal regulators, absorbing solar radiation during daylight hours and releasing it gradually after sunset, stabilizing temperatures and reducing frost risk. In modern sustainable design, this principle is known as thermal mass, widely used in advanced greenhouses and passive climate systems. Yet at Moray, this effect is achieved not with modern materials or sensors, but with stone, soil, and geometry alone. Archaeological excavations conducted from the late 20th century into the early 21st century added further layers to this mystery. Soil analysis revealed that different terrace levels contain compositions not native to the immediate region, indicating that soil was deliberately transported from multiple ecological zones. This is a critical detail. It suggests that the Inca were not merely adapting to their environment, but actively reconstructing it, bringing together variables from across their empire into a single, controlled testing ground. Some researchers propose that Moray functioned as an agricultural experimentation center, where crops were subjected to varying temperature and soil conditions to study their resilience and adaptability. This would effectively make it a pre-industrial equivalent of a modern research station, where controlled variables and repeatable conditions are essential. When compared directly to contemporary agricultural science, the parallels are striking. Modern experimental farms rely on climate-controlled chambers, sensor networks, and computational models to simulate environmental stress conditions. At Moray, the same principles appear to be implemented physically through architecture. Temperature variation, soil diversity, and moisture control are all present, yet achieved without any known measurement instruments or written documentation. There are no thermometers, no data records, no theoretical frameworks preserved. Only the system itself, functioning silently as it did centuries ago. The broader context of Andean terrace engineering reinforces this interpretation. Across the Sacred Valley, terraces exhibit consistent design principles that extend beyond simple cultivation. Their orientation maximizes solar exposure, their layered construction ensures efficient drainage, and their integration with irrigation channels allows precise water distribution. Excavations at Machu Picchu have shown that as much as 60% of the site's structure lies beneath the surface, forming a sophisticated drainage infrastructure composed of stone, gravel, and sand. This hidden system prevents water accumulation and stabilizes the terraces even under intense rainfall conditions. In modern civil engineering, similar subsurface drainage systems are considered essential for slope stability, yet they require detailed planning, surveying tools, and continuous maintenance. The Inca achieved comparable results using only natural materials and empirical design. Despite decades of research, a fundamental question remains unresolved. How did the Inca achieve such precise environmental control? Temperature gradients of 10 to 15 degrees Celsius are not accidental. They require careful calibration of depth, spacing, material composition, and airflow. Modern computational simulations have attempted to model Moray's thermal behavior, incorporating variables such as solar radiation and wind patterns. While these models can approximate the observed gradients, they often fail to reproduce the consistency measured in the field. In some cases, real-world data exceeds predicted values, suggesting that additional, less understood factors, possibly related to subsurface air circulation or microscale material interactions, are influencing the system. Comparisons with other ancient terracing systems further highlight the uniqueness of the Andean approach. Terraces in regions such as Southeast Asia or the Mediterranean were primarily designed for water management and land optimization. While effective, they do not demonstrate the same level of environmental manipulation. The Andean terraces, particularly at Moray, operate at both macro and micro scales, shaping not just the land but the climate itself. This level of integration is more characteristic of modern systems engineering than traditional agriculture. Equally remarkable is the durability of these structures. Many Andean terraces remain functional after more than 500 years, their drainage systems intact and their thermal properties still observable. In contrast, modern agricultural infrastructure often degrades within decades, requiring constant technological input to remain effective. The terraces function as self-regulating systems, balancing water flow, soil stability, and temperature without external intervention. This suggests not only advanced engineering, but a deep understanding of environmental equilibrium, an approach that modern sustainability efforts are only beginning to rediscover. What do you think? Was Moray truly an ancient agricultural laboratory? Or are we only just uncovering the surface of a far more advanced and forgotten science? Beneath a silent hill in eastern France, a technological paradox lay hidden for more than 2.5 millennia, an object that should not exist in the form we understand history. The moment archaeologists uncovered the burial chamber at Vix, they expected prestige, wealth, and ritual. What they did not expect was a machine, one that hinted at a level of metallurgical knowledge that feels disturbingly out of place in the 6th century BCE. At the center of this enigma stood the Vix grave wagon, a ceremonial vehicle that, upon closer inspection, revealed something far more unsettling, evidence of controlled alloy engineering in a world that supposedly lacked the tools to achieve it. The discovery began in 1953, when French archaeologist René Geoffroy led excavations at the Vix site located in Burgundy. Beneath a massive tumulus measuring nearly 40 meters in diameter, a burial chamber was revealed, remarkably intact, undisturbed, and filled with objects that immediately redefined the status of Iron Age. Inside lay the remains of a high-status woman, adorned with gold jewellery weighing over 400 grams, alongside imported luxury goods that traced connections far beyond local boundaries. Most striking among them was a colossal bronze crater, standing approximately 1.6 meters tall and weighing over 200 kilograms, widely believed to have originated from ancient Greece. Yet even this extraordinary vessel, the largest known from antiquity, would soon be overshadowed by the object beneath the burial platform, the wagon itself. Initially, the wagon appeared to be a standard elite chariot, a symbol of status commonly associated with high-ranking burials in Iron Age Europe. But as the excavation progressed, layer by layer, detail by detail, it became clear that this was something else entirely. The wooden structure had largely decayed, but its metallic framework remained. Iron-rimmed wheels, bronze fittings, and structural joints preserved with astonishing clarity. Measurements of the wheel diameter revealed near-perfect symmetry, with deviations so minimal that they fall within tolerances comparable to later pre-industrial craftsmanship. The axle alignment suggested deliberate engineering to reduce friction and distribute weight efficiently. This alone would be impressive, but it was the metallurgy that transformed the wagon from a cultural artifact into a scientific anomaly. Subsequent analyses, conducted decades after the initial excavation using modern techniques such as X-ray fluorescence and metallographic microscopy, revealed a complexity that continues to puzzle researchers. The bronze components of the wagon were not made from a single, uniform alloy. Instead, they exhibited deliberate variation in composition, primarily in the ratio of copper to tin. Some elements contained higher tin concentrations, reaching levels that would increase hardness and structural rigidity, while others showed lower tin content, resulting in greater flexibility and resistance to stress fractures. This is not random variation. It is functional metallurgy, the intentional tuning of material properties depending on mechanical demand. To understand the significance of this, it is necessary to consider the technological context of the Iron Age. At this time, metalworking was indeed advanced in certain respects, but it was largely based on empirical knowledge passed down through generations. There were no standardized temperature gauges, no chemical analysis, no formal understanding of phase diagrams or crystalline structures. Achieving consistent alloy compositions required precise control over smelting conditions, temperature, oxygen levels and cooling rates, all managed without instruments. Yet the Vix wagon demonstrates variations in alloy composition within a narrow margin, in some cases differing by only a few percentage points. Modern experimental reconstructions attempting to replicate these results using period-accurate furnaces have struggled to achieve the same level of consistency. Even more compelling is the evidence of thermal processing. Microstructural examination of certain iron components suggests that they underwent controlled heating and cooling cycles, processes analogous to quenching or annealing. These treatments can significantly alter the mechanical properties of metal, increasing hardness or relieving internal stresses. However, such processes require not only the ability to reach specific temperatures, but also the knowledge of when and how to cool the material to achieve the desired effect. In the absence of written records or surviving tools that indicate temperature measurement, the presence of such controlled treatment implies a level of experiential knowledge that borders on systematic science. Comparisons with other archaeological finds only deepen the mystery. Celtic metalwork from the same period, including weapons and tools, certainly displays skill and craftsmanship, but rarely this degree of material differentiation within a single object. In contrast, Mediterranean civilizations such as the Greeks and Etruscans were capable of producing large-scale bronze works, including statues and vessels like the Vix crater. Yet even in these regions, where metallurgical knowledge was more extensively developed and partially documented, the integration of multiple alloy types within a single mechanical system is uncommon. The Volkswagen appears to combine the artistic and material sophistication of Mediterranean craftsmanship with a functional engineering approach that is not clearly documented in either cultural sphere. Further excavations in the Vix region and beyond have provided additional data but no definitive parallels. Other high-status burials in Central Europe have yielded chariots or wagon components, yet none match the precise combination of alloy variation, structural balance, and evidence of thermal treatment observed here. Radiocarbon dating places the burial firmly around 530 BCE, aligning it with the late Hallstatt culture, a period known for increasing social complexity and long-distance trade networks. Isotopic analysis of metals used in Celtic artifacts suggests that raw materials may have been sourced from multiple regions, including alpine mining zones. This raises the possibility that the artisans responsible for the wagon had access not only to diverse materials, but also to a broader range of metallurgical traditions. But access alone does not explain execution. The leap from resource availability to precise alloy engineering remains unexplained. There is no clear archaeological record of incremental development leading to this level of sophistication. No series of prototypes, no gradual refinement visible across multiple sites. Instead, the Vix grave wagon stands as an isolated peak, a fully realized expression of a technological capability that appears suddenly and, in many ways, disappears just as abruptly. From a modern perspective, the Vix grave wagon reveals an early form of materials optimization, a principle central to contemporary engineering, where different alloys are deliberately chosen for strength, flexibility, and durability. The real mystery is not whether this was intentional, but how such precision was achieved without formal scientific frameworks. So in your view, is the Vix grave wagon the result of a lost knowledge system, or simply a rare peak of ancient craftsmanship? Share your thoughts in the comments below. There are artifacts that challenge history, and then there are those that quietly break it. The Pylos combat agate does not overwhelm with size or material value. It is small, almost fragile, easily overlooked among gold and weapons. Yet under magnification, it reveals something deeply unsettling, a level of precision, anatomical accuracy, and microscopic control that appears to belong to a world far more advanced than the Late Bronze Age. Measuring just 3.6 centimeters in length, The stone carries a complete battle scene carved with lines so fine they vanish to the naked eye. This is not simply art, it is a technical statement, one that raises a question modern science still cannot fully answer. How was this made? The story begins in 2015, just when archaeologists excavating near the Palace of Pylos in southwestern Greece uncovered what would later be named the Griffin Warrior Tomb. The burial, dated to approximately 1450 BCE, belonged to a high-status individual, quickly nicknamed the Griffin Warrior, due to an ivory plaque found beside him. Around the body were more than 1,000 artifacts, gold rings, weapons, mirror fragments, and intricately carved seal stones. At first, the agate in question attracted little attention. It was coated in thick limestone deposits, its surface unreadable. Only after months of careful cleaning did its true nature emerge, and when it did, it forced experts to pause. What they were looking at should not have been possible. As the incrustation was removed, a dynamic combat scene appeared. A warrior stands at the center, his body twisted in motion, muscles sharply defined, driving a blade into an opponent. Another fallen figure lies beneath them. The composition is fluid, almost cinematic, capturing a moment of violence frozen in stone. But the true shock came not from the scene itself, but from its scale. Individual details, facial features, strands of hair, muscle contours, measure less than 0.5 millimeter. Some incised lines are estimated to be as thin as 50 microns. Under normal viewing conditions, much of this detail is effectively invisible. It only fully reveals itself under magnification, suggesting that the artisan was working at a level of precision that challenges the limits of unaided human vision. The artifact is attributed to the Mycenaean civilization, a culture known for its palatial centers, linear B-script, and warrior elites. While Mycenaean craftsmanship was undoubtedly sophisticated, surviving seal stones and engravings from this period tend to follow consistent patterns, simplified forms, stylized anatomy, and relatively broad incisions. When compared side by side with other glyptic artifacts from the same era, often ranging between 1 to 5 centimeters in size, the difference becomes undeniable. Where most show limited depth and abstraction, the Pylos combat agate exhibits layered depth, proportional anatomy, and dynamic composition. In fact, its style aligns more closely with artistic principles that would only fully develop in classical Greece nearly 1,000 years later. This creates a chronological anomaly, an isolated leap forward in both artistic and technical execution. Yet a subsequent analysis compared the agate to hundreds of seal stones recovered from sites across Crete and mainland Greece, including Knossos and Mycenae. While Minoan artisans were known for more fluid and naturalistic designs, even their finest works fall short of the microscopic precision observed here. No transitional artifacts have been found, no gradual evolution leading to this level of detail. No workshop debris suggesting experimental stages. It appears fully realized, with no visible predecessors and no direct successors. This absence of technological continuity is critical. In most known cases of human innovation, advancements leave behind a trail of incremental improvements. Here, that trail is missing. At the center of the debate lies the most difficult question: how was the agate actually carved? The material itself presents the first challenge. Agate ranks between 6.5 and 7 on the Mohs hardness scale, making it significantly harder than bronze, the primary metal available at the time. This means that carving it would require not just tools but abrasives, likely powders such as emery, applied with consistent pressure and motion. Experimental archaeology has demonstrated that it is possible to engrave hard stones using bronze tools combined with abrasives. However, reproducing the precision seen in the Pylos combat agate has proven extraordinarily difficult. Modern craftsmen attempting replication often rely on steel tools, high magnification lenses, and stable working environments. Even then, maintaining line widths below 100 microns across a curved surface introduces micro-errors, slight tremors, and uneven depths or inconsistencies in spacing. Yet under microscopic analysis, the agate's lines remain remarkably consistent. There is little evidence of hesitation or correction. The cuts are clean, deliberate, and controlled. This suggests not only technical skill, but also a level of visual feedback that would be difficult to achieve without magnification. One proposed explanation is the use of primitive magnifying lenses, possibly made from polished quartz or glass. While convex lenses are known from later periods, there is no direct archaeological evidence confirming their use in Mycenaean engraving workshops. Another hypothesis suggests the use of extremely fine drill bits in combination with bow drills, allowing for controlled abrasion at small scales. Yet this still fails to explain how the artisan maintained such precision across complex intersecting lines without visual distortion or error accumulation. Even the idea of exceptional eyesight, an artisan with unusually acute vision, does not fully account for the mechanical consistency observed. High-resolution imaging has revealed that some engraved lines measure approximately 50 microns in width, with consistent depth profiles along their length. The spacing between parallel lines can be less than 100 microns, yet they do not merge or blur. On curved surfaces, maintaining such spacing requires continuous adjustment of angle and pressure. In modern micro-engraving, this is often achieved using stabilized mounts or guided systems. No such systems are known from the Late Bronze Age. Additionally, and the anatomical proportions depicted particularly in the torso and limbs demonstrate an understanding of human musculature that suggests either direct observation or an advanced artistic tradition, neither of which is well documented for this period at such a scale. The absence of intermediate artifacts combined with the technical difficulty of replication has led to two primary interpretations. The first is that the Pylos combat agate represents the peak of an undocumented tradition, a lineage of highly skilled artisans whose techniques were never widely adopted or preserved. The second is more radical, that modern assumptions about ancient technological limits are incomplete, and that certain capabilities, particularly in fine craftsmanship, have been underestimated or overlooked. In both cases, the artifact forces a reconsideration of what advanced truly means in a historical context. What do you think? Is this a lost technique or evidence that we are underestimating the capabilities of ancient civilizations? Share your thoughts in the comments below. A city that was never supposed to exist begins to reveal evidence that should never have been possible. Long treated as legend and immortalized in the verses of Homer, the site of Troy emerges not as a simple Bronze Age settlement, but as a layered anomaly, an archaeological record that repeatedly challenges the limits of what ancient civilizations were thought capable of achieving. Beneath the low hill of Hisarlik in northwestern Turkey lies a sequence of cities built, destroyed, and rebuilt over nearly 3,000 years, each layer preserving traces of knowledge that appear unexpectedly advanced for their time, and in some cases, disturbingly out of place. The location itself is not accidental. Positioned near the strategic Strait of Dardanelles, Troy occupied a critical gateway between the Aegean and the Black Sea, effectively controlling maritime trade routes that connected multiple civilizations. Geological reconstructions suggest that during the Bronze Age, the shoreline extended much closer to the city, potentially making Troy a coastal hub with direct access to shipping lanes. This geographic advantage helps explain its wealth and influence, yet it does not fully account for the precision and consistency of its urban planning across millennia. The modern rediscovery of Troy began in 1870, when Heinrich Schliemann initiated excavations at Hisarlik. Driven by a belief that Homer's epics described real events, Schliemann cut through the mound with little regard for later archaeological methods, uncovering a series of buried cities stacked atop one another. In 1873, he made his most famous discovery, a cache of artifacts he named Priam's Treasure. This collection included thousands of objects: gold diadems, necklaces, earrings, silver vessels, and finely crafted tools. At the time, Schliemann believed he'd found the wealth of the Trojan king described in legend. However, subsequent analysis would overturn that assumption. The treasure did not belong to the Troy of the Trojan War. Instead, it dated to a much earlier phase, Troy II, around 2500 BCE. This chronological shift created a paradox. The most technologically refined artifacts at Troy came not from its peak, but from one of its earliest known civilizations. Later excavations, led by Wilhelm Dörpfeld and Carl Blegen, revealed the full complexity of the site. At least 9 major settlement layers, Troy I through Troy IX, were identified, each representing a distinct period of occupation from roughly 3000 BCE to the Roman era. Despite the cycles of destruction and rebuilding, a striking pattern emerged. The orientation of structures remained remarkably consistent. Streets, walls, and gates were repeatedly aligned along similar axes, as if later builders had access to a hidden blueprint of earlier cities buried beneath their feet. Without modern surveying tools or subsurface imaging, this level of continuity remains difficult to explain. By the time archaeologists reached the layer known as Troy VI, dated to approximately 1700 to 1250 BCE, the scale of construction had become undeniable. Massive defensive walls composed of multi-ton limestone blocks surrounded the city, arranged in a form of cyclopean masonry comparable to structures found at Mycenae. Yet even within this comparison, Troy stands apart. The stones were fitted together with extraordinary precision, requiring no mortar to maintain stability for over 3 millennia. The walls were also built with a deliberate inward slope, a design that modern engineering recognizes as enhancing resistance to earthquakes and impact forces. Such structural awareness suggests either a long process of empirical refinement or a deeper understanding of physical principles that remains difficult to trace in the archaeological record. Evidence of destruction introduces another layer of uncertainty. The stratum identified as Troy 7a, often associated with the legendary Trojan War around 1200 BCE, shows signs of sudden and intense devastation. Burned debris, collapsed structures, and heat-altered materials have been found throughout the site. Some stones display partial vitrification, indicating exposure to temperatures that may have exceeded 1000 degrees Celsius. For comparison, typical open-air fires in ancient settlements rarely surpass 600 to 800 degrees. This discrepancy raises unresolved questions. Was the destruction caused by prolonged warfare, a large-scale urban fire, or conditions that produced unusually high and localized temperatures? Yet even these anomalies, precise urban continuity, advanced defensive engineering, and unexplained thermal damage, fade in comparison to the technological implications of the treasure itself. The so-called Treasure of Priam remains one of the most perplexing discoveries in the study of ancient metallurgy. Among its thousands of artifacts are gold diadems composed of hundreds of intricately assembled components, delicate chains formed with near-perfect uniformity, and finely detailed ornaments that exhibit techniques far beyond what is typically associated with the early Bronze Age. Metallurgical studies have identified processes such as granulation and filigree, methods requiring precise temperature control and exceptional manual skill. Granulation, in particular, involves attaching microscopic gold spheres to a surface without visible solder, a technique that would later be associated with Etruscan artisans over 1,000 years later. Yet at Troy, it appears fully developed as early as 2500 BCE. Comparative analysis deepens the mystery. In Mesopotamia, the royal tombs of Ur, dated to approximately 2600 BCE, yielded impressive gold artifacts, yet these tend to emphasize larger forms and simpler decorative techniques. In Egypt's Old Kingdom, goldwork demonstrates mastery in shaping and casting, but lacks the microscale precision seen in Trojan pieces. Even when compared to later Mycenaean artifacts from the 2nd millennium BCE, the jewellery of Troy too appears unusually refined. This is not merely advanced craftsmanship, it is advanced ahead of its expected time, without a clear developmental sequence leading to it. Chemical studies of the gold reveal additional complexity. Trace element analysis suggests that the material may have originated from multiple sources, possibly indicating long-distance trade networks or sophisticated resource acquisition strategies. Furthermore, the consistency in alloy composition across different objects implies controlled and standardized production methods. This level of uniformity suggests the presence of specialized workshops or organized systems of craftsmanship, rather than isolated experimentation. It points to a structured technological culture operating with repeatable precision. Modern attempts to replicate these techniques using materials and tools consistent with the early Bronze Age have achieved partial success, but reproducing the same level of consistency and intricacy remains difficult. This gap indicates that certain aspects of the original processes, whether related to temperature regulation, tool design, or material preparation, are not yet fully understood. In effect, the artifacts preserve the results of a technological system that cannot be entirely reconstructed. The question that follows is unavoidable. Where did this knowledge originate? Did it develop locally in a rapid and undocumented progression, or was it introduced through networks of exchange that have left little archaeological trace? Could it represent a fragment of a broader tradition of metallurgy that has since disappeared? Late 20th century excavations led by Manfred Kaufmann expanded the known extent of Troy, revealing a lower city that significantly increased estimates of its population and complexity. Within this expanded urban framework, the presence of such advanced metalworking raises further questions about social organization. Was this level of craftsmanship restricted to elite contexts, or was it part of a wider technological base? And if such knowledge existed, why does it appear so suddenly and vanish without clear continuity? So do you think Troy is evidence of an advanced civilization ahead of its time, or just a mystery we haven't fully understood yet? Share your thoughts in the comments below. Something small, silent, and almost invisible to the untrained eye may represent one of the greatest technological paradoxes of the ancient world. Not a monument towering above the landscape, not a temple carved into stone, but a collection of carefully crafted cubes, each nearly identical, each balanced with a level of precision that seems to defy the technological limits of its time. These are the standardized weights of the Indus Valley civilization, and the deeper they are studied, the more they challenge the very idea of what ancient engineering was capable of achieving. The story begins in the early 20th century, when large-scale excavations at Mohenjo-Daro and Harappa first revealed the scale of a lost urban civilization. Under the direction of John Marshall, archaeologists uncovered not only vast cities with grid-like street planning and advanced drainage systems, but also hundreds of small stone objects that at first seemed insignificant. These cubes, often made of dense chert, were discovered in residential areas, storage facilities, and what appeared to be trading zones. As further excavations expanded into other major sites such as Lothal, a port believed to be connected to maritime trade, and Holavera, known for its remarkable water management systems, the same pattern emerged again and again. Across distances exceeding hundreds of kilometers, the same types of weights appeared, sharing not just similar shapes, but nearly identical mass values. As systematic measurements were conducted, a hidden mathematical order revealed itself. The weights followed a structured progression based primarily on binary scaling: 1, 2, 4, 8, 16, 32, and extended into decimal multiples, suggesting a sophisticated numerical framework underlying their use. But what astonished researchers most was not the system itself, but its consistency. Comparative studies of weights from different layers, different cities, and different excavation campaigns revealed deviations typically within 1 to 2%, with some specimens showing even tighter tolerances. For a civilization dating back over 4,000 years, this level of uniformity is extraordinary. In contrast, weight systems in Mesopotamia, such as the shekel, varied significantly between city-states and evolved over time, often requiring conversion systems. Even in ancient Egypt, where measurement played a crucial role in architecture and administration, regional and chronological variation is clearly visible. The Indus system, by comparison, appears almost immune to such drift, unchanged across both space and centuries. Yet beneath this numerical precision lies a deeper and far more unsettling mystery: the technology of manufacture itself. The majority of these weights were crafted from chert, a material with a hardness approaching 7 on the Mohs scale. This places it far beyond the easy working range of copper, the primary metal tool available to Harappan craftsmen. Shaping chert into even a rough form requires sustained abrasion, using harder materials, careful grinding, and significant time investment, and yet, the finished weights display a level of geometric precision that goes far beyond what such processes would normally produce. Their faces are remarkably flat, their edges sharply defined, and their overall proportions strikingly regular. More importantly, their mass is controlled with a consistency that implies not only precise shaping, but a deep understanding of material density, internal structure, and error correction. Modern experimental archaeology has attempted to replicate these weights using only tools and techniques available during the Bronze Age. Researchers have employed copper implements, abrasive sands, and manual polishing to recreate chert cubes of similar size. While these experiments can approximate the general shape, they consistently fail to reproduce the same level of uniformity and mass across multiple samples. Even under controlled laboratory conditions, minor variations in density, microfractures within the stone, or inconsistencies in surface finishing lead to measurable discrepancies. And yet, the Harappan weights demonstrate a level of repeatability that suggests these variables were not only recognized, but systematically minimized, if not fully controlled. This creates a paradox that has yet to be resolved. To achieve such precision, one would expect the presence of advanced calibration tools, standardized molds, or at the very least a central reference object, a master weight against which all others could be compared. However, no such artifact has ever been conclusively identified, nor has any central workshop or manufacturing hub been discovered that could account for large-scale controlled production. Instead, the weights appear across dozens of sites, each maintaining the same standard, as though the knowledge required to produce them was both widespread and perfectly preserved. One proposed explanation is the use of iterative calibration, where each weight is repeatedly adjusted by comparison to another until a balance is achieved. But this method, when applied across multiple generations and locations, inevitably introduces cumulative error, a phenomenon known as calibration drift. In most historical systems, this leads to gradual divergence over time. Yet in the Indus Valley, no such divergence is clearly observed. Weights from early and late phases remain consistent within narrow margins. Another hypothesis suggests volumetric control, perhaps using water displacement to ensure consistent volume before final shaping. Given the relatively stable density of chert, this could approximate mass control. But such a technique would require highly precise containers, stable environmental conditions, and standardized procedures, none of which have been definitively identified in the archaeological record. Each new excavation has only deepened the mystery. At Lothal, weights were found near dockyards and storage facilities, indicating their role in regulating trade. At Dolavira, they appear in structured administrative contexts, suggesting using governance or taxation. Across more than 100 known Indus sites, similar weights have been documented, reinforcing the idea of a civilization-wide system of standardization. Some researchers have even proposed that this system may have facilitated long-distance trade beyond the Indus region, and serving as a reliable standard in exchanges with distant cultures. And yet one critical element remains missing: explanation. The Indus script found on seals and artifacts throughout the civilization has not been conclusively deciphered. If it contains instructions, definitions, or theoretical principles related to measurement and manufacturing, they remain inaccessible. Without this key, we are left with physical evidence of a system whose underlying logic is only partially understood. Then, around 1900 BCE, the system disappears. As the Indus Valley civilization declined, its cities were gradually abandoned, its trade networks disrupted, and its technological systems lost. The standardized weights, once so consistent and widespread, vanish from the archaeological record. Later cultures in the region do not immediately replicate their level of precision. There is no clear transition, no gradual evolution, only a sudden absence. It is as if the knowledge required to create and maintain this system was not only lost, but never fully transmitted beyond the society that sustained it. What do you think allowed this civilization to achieve such impossible precision? And why did this entire system of knowledge completely disappear? Share your thoughts in the comments below. A fragment no larger than a human hand, cylindrical, silent, and easily dismissed, contains within it a mechanical signature that should not exist. Hidden among the debris of ancient construction zones, Egyptian stone drill cores appear, at first glance, to be nothing more than the waste product of a forgotten process. But under close inspection, they reveal something deeply unsettling, a level of precision and cutting efficiency that seems to defy the technological limits of their time. These objects do not simply belong to history, they challenge it. The story unfolds on the vast limestone expanse of the Giza Plateau, where some of the most iconic structures in human history were erected more than 4,000 years ago, amid pyramids aligned with celestial precision and statues carved from granite and diorite, materials that even modern industry approaches with caution. Archaeologists uncovered something far less imposing, but arguably more perplexing. Small cylindrical cores, extracted during drilling operations, were found scattered among quarry debris and embedded within unfinished stone blocks. Additional discoveries at Saqqara and Abu Rawash reinforce a critical point. This was not an experimental technique, but a standardized industrial process used repeatedly across different sites and construction phases. The turning point in understanding these artifacts came with the meticulous work of Flinders Petrie in the late 19th century. Unlike earlier observers, Petrie approached the cores with a scientific mindset, measuring, cataloguing, and comparing them with an engineer's precision. What he documented would become one of the most debated observations in the study of ancient technology. On multiple granite drill cores recovered from Giza, Petrie identified a series of spiral grooves wrapping around the surface in a continuous helical pattern. These grooves were not random scratches. They were evenly spaced, deeply incised, and astonishingly regular, bearing a striking resemblance to the threads of a modern machine screw. Yet the true anomaly was not their appearance, but their geometry. By measuring the spacing between these grooves, Petrie concluded that the drill advanced into the stone at a rate of approximately 2 to 3 millimeters per revolution. In isolation, this figure might seem trivial, but when placed against the physical reality of granite, a composite rock containing quartz crystals with a Mohs hardness of around 7, it becomes extraordinary. Granite resists cutting with remarkable tenacity. Even today, industrial drilling requires diamond-tipped tools, high rotational speeds, and precisely controlled pressure to achieve efficient penetration. Modern benchmarks provide a crucial comparison. Under controlled laboratory conditions, diamond drilling into granite typically achieves a feed rate between 0.02 and 0.1 millimeters per revolution. These values are not arbitrary. They represent the balance between cutting efficiency, tool wear, and material resistance. Against this standard, and the 2 to 3 millimeters per revolution implied by the Egyptian cores is not simply higher, it is dramatically, almost impossibly higher, exceeding modern expectations by factors of 20 to 100 times. This single measurement transforms the drill cores from minor archaeological artifacts into a profound engineering mystery. The conventional explanation offered by Egyptology centers on the use of tubular copper drills combined with abrasive materials such as quartz sand. In this model, the copper acts as a soft carrier, embedding the abrasive particles that perform the actual cutting. Over time, the abrasive grinds away the stone, producing a cylindrical hole and leaving behind a core. This explanation is supported by artistic depictions and experimental reconstructions. However, while such experiments can replicate the existence of drilled holes, they consistently fail to reproduce the defining feature of the ancient cores, the precise, continuous spiral grooves. Modern experimental results typically produce irregular surfaces with discontinuous scratch marks, reflecting the chaotic motion of loose abrasive particles. By contrast, the grooves observed on ancient cores are uniform, deeply cut, and maintain a consistent pitch over multiple rotations. This suggests a level of mechanical control that goes far beyond simple abrasive grinding. The cutting action appears directional, stable, and sustained, more akin to a modern machining process than a rudimentary manual technique. Microscopic analysis intensifies this contradiction. The grooves are not superficial abrasions. They penetrate into the stone with measurable depth, and their edges are sharply defined rather than fractured. This indicates that material was removed in a controlled and continuous manner, not shattered or chipped away. Furthermore, the consistency of the helical pattern implies that the drill maintained a steady rotational axis and a uniform downward force throughout the process. Achieving such stability would require a rigid system, one capable of minimizing vibration and maintaining alignment over time. Evidence from excavation sites adds another layer of complexity. At Saqqara, partially drilled holes preserved in unfinished artifacts reveal internal surfaces that are remarkably smooth and geometrically consistent. In some cases, the diameter of the hole remains constant over several centimeters of depth, suggesting that the drilling tool maintained precise alignment without deviation. In modern engineering, such results are typically achieved using fixed drill presses, guide mechanisms, and hardened materials. Yet no definitive evidence of such systems has been found in the archaeological record of ancient Egypt. Material science further complicates the picture. Copper, the primary metal associated with Egyptian tools of this period, has a Mohs hardness of approximately 3, far softer than the quartz crystals embedded within granite. For the abrasive drilling model to account for the observed results, the abrasive particles would need to be consistently distributed and retained under significant pressure, while the tool itself would need to maintain structural integrity despite rapid wear. Even under ideal conditions, achieving a feed rate of several millimeters per revolution with this method remains highly improbable. In response to these challenges, alternative hypotheses have emerged. Some researchers propose that the Egyptians may have used harder abrasives, such as corundum, which has a Mohs hardness of 9, or even naturally occurring diamonds. Others suggest the existence of more advanced mechanical systems, devices capable of maintaining continuous rotation at higher speeds, possibly using flywheels or coordinated human power to generate sustained torque. There are also theories that propose unknown techniques of material treatment or tool reinforcement. However, despite decades of experimentation, no single explanation has successfully reproduced all the observed characteristics simultaneously. The groove depth, spacing, continuity, and precision remain unmatched. What kind of technology could create such impossible spiral grooves? And are we still missing a crucial piece of the puzzle? Share your thoughts below. It begins not with what you see, but with what you hear. Deep within the colossal stone labyrinth of Karnak Temple, a single human voice can travel farther than it should, remain clearer than it has any right to be, and in certain places seem almost guided. No visible mechanism, no curved amphitheatre walls, no domes. And yet something in this ancient structure appears to shape sound with unsettling precision. The question is simple, but deeply unsettling. Did the builders of Karnak understand acoustic geometry in ways we still struggle to explain? Rising from the eastern bank of the Nile in Luxor, Karnak is not a single temple, but a vast religious complex constructed and expanded over nearly 2,000 years by the rulers of ancient Egypt. Covering more than 200 hectares, it is one of the largest sacred sites ever built, and at its core stands the Great Hypostyle Hall, an architectural space so immense that structures like Notre Dame Cathedral could fit within its footprint. The hall spans roughly 5,000 square meters and contains 134 sandstone columns arranged in 16 rows. The central columns rise to over 20 meters in height, while the outer ones stand slightly shorter, forming a subtle elevation gradient that has long been interpreted as symbolic hierarchy. Yet this vertical modulation may also play a role in guiding airflow and, more intriguingly, sound propagation. The acoustic mystery of Karnak did not emerge from a single discovery, but from repeated, consistent observations across centuries. And early European explorers in the 19th century recorded unusual auditory effects within the hall. Voices carrying farther than expected, echoes behaving irregularly, and certain positions where speech seemed amplified without effort. In the early 20th century, during excavation and restoration campaigns led by Georges Legrain, the focus remained on structural preservation and epigraphy, yet anecdotal reports of strange sound behavior persisted among workers and visitors. Later, teams associated with the Centre Franco-Égyptien d'études des Temples de Karnak began documenting spatial precision and architectural alignment with greater rigor, indirectly reinforcing the idea that the layout of the hall was far from accidental. By the late 20th and early 21st centuries, limited acoustic experiments, ranging from controlled voice projection tests to basic sound pressure measurements, began to reveal measurable anomalies. localized increases in sound intensity by several decibels, directional clarity along specific axes, and abrupt transitions between zones of intelligibility and acoustic silence. In some tests, a human voice spoken at normal volume could be understood clearly at distances exceeding 30 to 40 meters, while moving just 2 to 3 meters sideways caused that same voice to dissolve into diffuse reverberation. These are not vague impressions. They're repeatable, position-dependent effects. At the center of this mystery lies perhaps the most compelling question of all: the role of geometric precision in shaping acoustic behavior. At first glance, the hypostyle hall appears as a simple grid, a forest of evenly spaced stone columns extending in ordered rows. But closer inspection reveals a far more sophisticated spatial logic. The spacing between columns, while broadly consistent, contains subtle variations that influence how sound waves propagate and interact. The central nave, elevated and more widely spaced, forms a longitudinal corridor that may act as a preferential channel for sound transmission, allowing waves to travel with reduced interference. In contrast, the denser outer rows create a layered acoustic boundary, scattering stray reflections and preventing chaotic reverberation from overwhelming the space. This dual structure arrangement, open central axis and compressed lateral zones, mirrors, in a primitive yet striking way, yet the zoning strategies used in modern acoustic engineering. From a contemporary scientific perspective, this begins to resemble controlled wave interference. In modern concert halls, designers use advanced computational modeling to manipulate geometry so that sound waves arrive coherently at specific points, enhancing clarity and presence. This often involves adjusting distances down to centimeters, calculating reflection angles, and predicting interference patterns across frequencies. Yet Carnac achieves a comparable effect on a monumental scale, without any known mathematical framework, without documented acoustic theory, and without tools that could measure wavelength, phase, or frequency in the modern sense. And still, yet the result suggests a functional understanding of spatial acoustics, whether intentional or empirical, that challenges our assumptions about ancient technological limits. The numbers only deepen the puzzle. With 134 columns, each several meters in diameter and arranged across a vast enclosed space, the hall should theoretically produce chaotic scattering. In modern environments with similar density, industrial storage facilities, transit halls, or structural grids, sound becomes rapidly diffuse, losing coherence within a few meters. But Carnac behaves differently. Instead of uniform acoustic decay, it produces selective amplification. Researchers have proposed that the column grid creates interference patterns, zones where sound waves reinforce each other, increasing amplitude, and zones where they cancel out, still producing silence. This would explain the existence of acoustic hotspots and dead zones within the hall. But for such patterns to emerge consistently across a space of this scale, the geometric arrangement must be extraordinarily precise, not just visually symmetrical, but acoustically tuned. Then there is the surface itself. Every column in the hypostyle hall is covered in deeply carved hieroglyphs and reliefs, forming a complex microtexture that interacts with sound at a smaller scale. In modern acoustic design, similar irregular surfaces are used as diffusers, structures that scatter high-frequency noise while preserving overall clarity. At Carnac, this effect may occur naturally. Higher frequencies are broken up, reducing harsh echoes, while lower frequency components of the human voice, typically between 100 and 300 Hz, are allowed to propagate more efficiently through the space. This creates a filtering effect, enhancing intelligibility while suppressing acoustic chaos. Yet again, the question remains unresolved. Was this an intentional design feature, or an accidental byproduct of decorative tradition. When compared to other ancient acoustic achievements, the uniqueness of Karnak becomes even more apparent. The theatre of Epidaurus in Greece is often cited as a masterpiece of ancient sound engineering, where a whisper can travel over 60 meters thanks to carefully designed open-air geometry and tiered seating. Roman amphitheatres use curved walls and reflective materials to project sound outward with efficiency. In both cases, the acoustic principles are visible, intentional, and reproducible. Karnak, by contrast, lacks all of these conventional elements. It is enclosed, densely obstructed, and geometrically rigid, yet it produces an effect that is arguably more mysterious. There are no curved reflectors, no designed focal points, no textual evidence describing acoustic intent. And still, the phenomenon persists. Modern simulations have attempted to reconstruct the hypostyle hall using digital models, incorporating estimated material properties of sandstone and approximated spatial dimensions. However, these models often fail to reproduce the precise localization of sound amplification without introducing assumptions that cannot be verified archaeologically. This gap between simulation and reality suggests that critical variables, perhaps minute alignment deviations, surface irregularities, or even environmental conditions such as temperature gradients, play a role that is not yet fully understood. It also raises the possibility that the acoustic behavior of Karnak is emergent, arising from the interaction of multiple factors rather than a single design principle. Beyond physics and geometry lies a deeper human dimension. The hypostyle hall was not an empty structure. It was a ceremonial environment, a stage for rituals, processions, and spoken invocations. If certain positions allowed a priest's voice to carry clearly across a large gathering, while other positions suppressed competing sounds, the result would have been profoundly impactful. A voice emerging from within the towering columns, amplified by unseen forces, would not feel like a human voice. It would feel like something else entirely, something divine. In this context, the unnatural amplification effect becomes more than an acoustic curiosity. It becomes a tool of experience, shaping perception, reinforcing authority, and blurring the boundary between the physical and the sacred. Do you think this is merely a coincidence? Or did the ancient Egyptians truly master acoustic science in ways we still don't fully understand? Share your thoughts in the comments below. A language we can pronounce, yet one that refuses to reveal its meaning, etched with a level of precision that feels disturbingly out of place in the ancient world. Long before Rome imposed its linguistic order across the Italian peninsula, the civilization known as the Etruscan civilization left behind thousands of inscriptions, silent, fragmented, and unnervingly exact. Today, linguists can sound out much of the Etruscan language thanks to its connection with the Greek alphabet, yet the meaning remains largely inaccessible. But beyond the linguistic mystery lies something even more unsettling: the physical execution of these texts. Across stone, bronze, gold, and ceramic surfaces, Etruscan inscriptions display a level of engraving precision that challenges what we believe Iron Age tools were capable of achieving. This is not simply a lost language, it is a lost technique. The first clues emerged not from a single discovery, but from a pattern observed across multiple excavations in central Italy during the 19th century. Early digs in Tarquinia and Cerveteri revealed tombs filled with inscribed objects, funerary markers, ritual vessels, and painted walls bearing lines of text. At first glance, these inscriptions appeared typical of ancient Mediterranean cultures. But as archaeologists began documenting them systematically, a subtle inconsistency became impossible to ignore. The engraved characters, often less than a few millimeters in depth, were astonishingly uniform. Stroke widths remained consistent across entire inscriptions. Curves were smooth and uninterrupted, and angular cuts showed no evidence of hesitation or correction. In an era when metal tools were hand-forged and prone to variation, such consistency should have been rare. Instead, it was the norm. By the mid-20th century, more controlled excavations began to provide clearer data. One of the most significant moments came in 1964, when Italian archaeologist Massimo Pallottino led excavations at the coastal sanctuary of Pyrgi. There, 3 thin sheets of gold were uncovered, now known as the Pyrgi tablets, 2 inscribed in Etruscan and 1 in Phoenician. These tablets, dated to around 500 BCE, were expected to unlock the language through direct comparison. While they did provide limited insights into religious vocabulary, their greater impact lay elsewhere. Under magnification, the engraved letters revealed an extraordinary level of control. Each incision maintained a consistent depth, estimated at fractions of a millimeter, with edges so clean they appeared almost machined. Gold, while softer than bronze or iron, is also highly malleable, meaning that uneven pressure typically results in deformation around the cut. Yet the Pyrgi inscriptions show minimal surface distortion, suggesting a technique capable of distributing force with remarkable precision. Subsequent analyses compared these engravings to contemporary Greek and early Roman inscriptions. Greek stone carvings from the same period often display visible tool marks, variations in pressure, minor slips, and occasional corrections where lines were reworked. Early Latin inscriptions, though increasingly refined, still exhibit irregular spacing and inconsistent stroke depth. The Etruscan examples, by contrast, appear almost standardized. In some cases, statistical measurements of letter proportions, height, width, and spacing show deviations of less than 5% across entire texts. Such uniformity implies either an exceptional level of craftsmanship or the use of guiding systems that have left no direct trace in the archaeological record. The mystery deepened with the examination of bronze artifacts. Etruscan bronze mirrors and ritual objects, many of which bear inscriptions, were recovered in large numbers throughout the 20th century. Unlike gold, bronze presents a harder surface, requiring greater force and more durable tools to engrave, yet the inscriptions on these objects maintain the same sharpness and consistency observed on softer materials. Our microscopic studies conducted in the late 20th century identified clean incision walls with minimal microchipping, an indication that the cutting edges used were both sharp and stable over extended use. This is particularly puzzling given the limitations of Iron Age metallurgy. While iron tools were available, their hardness and durability depended heavily on forging techniques that were still evolving. To achieve repeated precision cuts on bronze without rapid tool degradation would have required either advanced heat treatment methods or frequent tool replacement, neither of which is well documented in Etruscan contexts. Stone inscriptions present an even more complex challenge. Many Etruscan texts are carved into volcanic tuff, a material softer than granite but still resistant enough to require controlled force. In tomb complexes such as those at Tarquinia, inscriptions carved into tough walls retain crisp edges after more than 2,500 years. Weathering has affected surrounding surfaces, yet the carved lines often remain sharply defined. This suggests that the initial cuts were not only precise but also deep enough and clean enough to resist gradual erosion. Comparisons with similar carvings from other Italic cultures show a noticeable difference. Where non-Etruscan inscriptions have softened into indistinct grooves, Etruscan text frequently remains legible. The implication is that technique, not just material, played a decisive role. Excavations in the late 20th and early 21st centuries have continued to reinforce this pattern. At sites such as Veii and Vulci, or archaeologists have uncovered additional inscribed objects across a range of contexts: domestic, funerary, and religious. In each case, the same characteristics emerge: uniform stroke depth, consistent spacing, and a lack of visible error. Even on curved surfaces such as ceramic vessels, the inscriptions maintain alignment and proportional balance. Experimental archaeology has attempted to replicate these results, using reconstructed Iron Age tools, but with limited success. While skilled artisans can approach the visual appearance of Etruscan inscriptions, achieving the same level of microscopic consistency remains difficult without modern instrumentation. One hypothesis suggests the use of preliminary guidelines, lightly incised or marked before final engraving, to ensure alignment and spacing. However, in many cases, and no such guidelines are visible even under magnification. Another possibility involves the use of abrasives, fine sand or emery, to assist in cutting, effectively turning the process into a controlled grinding rather than a simple incision. This could explain the smoothness of the cuts, but does not fully account for their uniform depth. A more speculative theory proposes the existence of specialized tools with standardized tips, capable of producing consistent strokes regardless of operator variation. Yet no such tools have been definitively identified in Etruscan archaeological assemblages. What makes this phenomenon particularly compelling is its consistency across time and material. From the earliest inscriptions in the 8th century BCE to later examples just before the assimilation of Etruscan culture into Rome, the same level of precision persists. This suggests not a brief technological anomaly, but a sustained tradition, one that was taught, refined, and maintained over generations. And yet, unlike monumental architecture or large-scale engineering, the tools and methods behind this tradition have left almost no trace. Do you think the Etruscans truly possessed a lost technology? Or are we simply underestimating their abilities? Share your thoughts in the comments below. At first, it looks like nothing more than a small bronze figure. Ordinary, almost insignificant in scale. Yet from the moment it was uncovered at Mohenjo-Daro, it carried a quiet contradiction that refused to be ignored. Barely over 10 centimeters tall, the dancing girl appears simple at first glance. But the deeper scientists looked, the more unsettling it became. The metal, the precision, the durability, none of it fully aligns with what we expect from the Indus Valley civilization over 4,000 years ago. It is not just an artifact, it is a question, one that suggests something about the ancient world may still be missing. The story begins in 1926, during one of the earliest large-scale excavations led by Ernest J. H. Mackay under the direction of John Marshall. Mohenjo-Daro, one of the principal urban centers of the Indus Valley civilization, had already revealed an astonishing level of planning. Grid-based streets, drainage systems, standardized bricks. But it was within a modest residential structure that this small bronze figure was uncovered, lying among ordinary debris. At the time, it was catalogued as a curious artifact, notable for its form, but not yet understood for its deeper implications. Only decades later, as analytical techniques advanced, would its true significance begin to emerge. Subsequent archaeological campaigns throughout the 1920s and 1930s expanded the known extent of Mohenjo-Daro, revealing workshops, furnaces, and evidence of widespread craft production. Yet nothing discovered during these excavations quite matched the refinement of the dancing girl. While copper tools, beads, and simpler cast objects were found in significant numbers, they often displayed the expected limitations of early metallurgy: uneven surfaces, casting flaws, and inconsistent material composition. The figurine, by contrast, seemed to exist in a different category altogether. It was not merely better, it was fundamentally more controlled. The turning point came with the application of modern scientific analysis in the late 20th century. Using techniques such as X-ray fluorescence and metallographic microscopy, researchers began to examine the internal composition of the statue. What they found was unexpected. The metal was not pure copper, but a carefully balanced alloy containing tin, arsenic, and trace amounts of other elements. In some analyses, this tin content appeared to range between roughly 1 and 12%, a proportion known to significantly enhance hardness while lowering the melting point to a more manageable range, often around 900 to 1000 degrees Celsius. Arsenic, even in small quantities, improves the fluidity of molten metal, allowing it to fill fine molds with remarkable precision. Lead, if present, can reduce internal stresses and minimize shrinkage defects. Individually, these effects are well understood in modern metallurgy, but together, in a single artifact dated to around 2500 BCE, they raise a critical question. How was this combination achieved? Because the alloy does not appear random. Its distribution is relatively uniform, suggesting that the molten metal was thoroughly mixed before casting. This level of homogeneity requires sustained high temperatures and controlled conditions, factors that are difficult to reconcile with the archaeological evidence of relatively simple furnaces at Mohenjo-Daro. To understand the scale of this anomaly, it is necessary to compare it with other Bronze Age civilizations. In Mesopotamia, bronze artifacts from comparable periods frequently exhibit clear signs of inconsistent alloying, regions of varying composition, visible porosity caused by trapped gases, and structural weaknesses resulting from uneven cooling. Similarly, early metalwork from ancient Egypt often required extensive post-casting finishing, with surfaces that reveal the limitations of less controlled processes. In contrast, the dancing girl shows relatively smooth surfaces and a level of detail that suggests the metal flowed cleanly into the mold, capturing fine features without significant defects. Under magnification, its microstructure lacks the large, irregular crystalline formations typical of poorly controlled cooling, instead indicating a more refined thermal process. But it is not just how the statue was made, it is how it has survived that deepens the mystery. Over 4,000 years, buried beneath layers of soil exposed to moisture, salts, and shifting environmental conditions, most bronze artifacts would undergo significant degradation, a phenomenon known as bronze disease, driven by chemical reactions between copper, oxygen, and chlorides, can slowly destroy an object from within, leaving it fragile and unstable. Yet the dancing girl remains remarkably intact. A patina has formed as expected, but beneath it the structure holds. The metal has endured. Modern corrosion studies suggest that certain alloy compositions can significantly influence long-term durability. A balanced ratio of tin can increase resistance to oxidation, while trace elements such as arsenic may contribute to the formation of protective surface layers that inhibit further corrosion. If the composition of the dancing girl falls within such an optimal range, it could explain its survival. But this leads to a deeper question, one that archaeology alone cannot answer. Was this durability intentional? Did the artisans of the Indus Valley understand, even empirically, how to create a metal that could resist decay over millennia? Or was this the result of repeated experimentation, a process of trial and error that eventually produced an alloy of exceptional stability? Excavations provide only fragments of an answer. Despite decades of work at Mohenjo-Daro, including renewed studies using modern surveying and analytical methods, there is no clear evidence of large-scale metallurgical infrastructure capable of consistently producing such refined alloys. Small furnaces and casting residues have been identified, but they do not fully account for the level of control implied by the dancing girl. Even more puzzling is the absence of a clear technological progression. There are no obvious predecessors, no sequence of increasingly sophisticated artifacts leading up to this point. Instead, the figurine appears almost fully formed, as though it represents the peak of a tradition that has otherwise vanished from the record. When placed alongside later metallurgical achievements, the anomaly becomes even more pronounced. The bronze works of ancient China's Shang dynasty, emerging more than 1,000 years later, demonstrate advanced casting techniques, but are supported by extensive archaeological evidence of molds, workshops, and production systems. Classical Greek bronze sculpture, appearing nearly 2,000 years after the Dancing Girl, reflects a long and well-documented evolution of both artistic and technical knowledge. In both cases, innovation is visible, traceable, and cumulative. But in the Indus Valley, the pattern breaks. The Dancing Girl stands alone, refined, controlled, and unexplained. Some researchers suggest that the answer may lie in the structure of Indus society itself. Unlike the centralized empires of Egypt or Mesopotamia, the Indus world appears to have been organized through a network of interconnected urban centers, unified by standardized systems of measurement and craft production. Metallurgical knowledge may have been similarly distributed, maintained by specialized artisans whose techniques were transmitted through practice rather than written instruction. Given that the Indus script remains undeciphered, any record of such knowledge may simply be inaccessible. Others propose that the composition of the alloy may have been influenced by specific ore sources, naturally containing the elements needed to produce a more durable metal. And yet, even these explanations leave the central paradox unresolved. The Dancing Girl embodies a convergence of material composition, casting precision, and long-term durability that does not align easily with established models of technological development. Its alloy suggests control, its structure suggests intention, its survival suggests understanding, and yet, the system that produced it remains invisible. So what do you think? Does the Dancing Girl represent a lost technology, or simply a rare coincidence in history? Share your thoughts in the comments below. A machine that remembers direction, without ever sensing it. No magnet, no stars, no external reference. Just motion correcting motion, endlessly, invisibly. Long before humanity learned to trust the pull of the Earth's magnetic field, ancient China may have created something far stranger. A device that could preserve orientation purely through mechanics. It is known as the south-pointing chariot, and if the historical accounts are even partially accurate, it represents one of the most intellectually unsettling technologies ever attributed to the ancient world. Because it does not detect direction, it preserves it. The earliest traces of this device do not come from excavation, but from texts, records compiled centuries after the supposed invention, referencing reconstructions during the era of Three Kingdoms. The most frequently cited figure is Ma Jun, an engineer described as having rebuilt the chariot for imperial use. According to these accounts, the vehicle carried a human figure mounted on top, its arm extended outward, always pointing south. Not guided, not corrected, simply fixed. Turn the chariot left and the figure rotates right. Turn right, it rotates left. Spin the entire structure, and somehow, through hidden internal logic, the figure resists the motion and returns to its original orientation. This was not navigation in the conventional sense. It was something far more abstract. A system that continuously cancels its own movement. At the core of this phenomenon lies what modern engineers identify as a differential gear system, a concept that would not formally emerge in Western mechanical theory until more than a millennium later. In modern vehicles, a differential allows wheels to rotate at different speeds when turning. But in the south-pointing chariot, this principle appears to have been used in reverse, not to accommodate motion, but to negate it. When the chariot moves forward in a straight line, both wheels rotate equally, and the system remains neutral. But the moment the chariot turns, the imbalance in wheel rotation is captured and transferred through a network of gears. That imbalance becomes information. And that information is used to rotate the figure in the opposite direction of the turn. Every action produces an equal and opposite correction. Over time, the system accumulates no net change in orientation. It remembers where it started, without ever knowing where it is. This is where the mystery becomes deeply technical and deeply problematic. Unlike the later magnetic compass, which relies on the Earth's magnetic field as a constant external reference, the south-pointing chariot is a closed system. It does not correct itself based on the environment. It corrects itself based on its own movement. This means that its accuracy depends entirely on internal precision. And here, modern data introduces a paradox. Experimental reconstructions in the 20th century, particularly in Japan in the 1930s and later in China, demonstrated that such a system can function, but only under near-perfect conditions. Tests show that a difference of just 1% in wheel diameter or rotational consistency can lead to directional drift of 3 to 5 degrees per kilometre. Over a distance of 10 kilometres, this could result in an error exceeding 30 degrees. On uneven terrain, where slippage and resistance vary constantly, deviation can exceed 10 degrees in just a matter of minutes. Yet historical accounts imply far greater reliability. Some descriptions suggest the chariot maintained consistent orientation over long ceremonial routes, or even during extended travel. If this is accurate, then the mechanical tolerances required would be extraordinarily high, approaching levels of precision not typically associated with ancient manufacturing. Archaeological findings complicate this further. While no complete south-pointing chariot has ever been discovered, excavations across China, particularly from the Han Dynasty, have yielded bronze gears, axles, and mechanical components that demonstrate advanced craftsmanship. However, detailed analysis of these artifacts reveals inconsistencies, and gear teeth are often slightly uneven, casting imperfections are visible. Axle alignments are not perfectly symmetrical. These are minor flaws by ancient standards, but catastrophic for a system that depends on exact rotational equivalence. This contradiction creates technological tension. If the chariot truly worked as described, then ancient engineers achieved a level of precision that exceeds what surviving artifacts suggest. But if they did not, then the historical descriptions must be exaggerated or misunderstood. Comparisons with other ancient devices deepen the mystery. The Antikythera mechanism, dated to the 2nd century BCE, contains over 30 interlocking gears and could predict astronomical cycles with remarkable accuracy. However, it operated in a static environment. It was not subject to vibration, terrain variation, or continuous motion. The south-pointing chariot, by contrast, would have functioned while moving, constantly adjusting, constantly correcting. The difference is not just mechanical, it is conceptual. One calculates, the other compensates. Modern reconstructions highlight this challenge. Some models, built with high-precision materials and calibrated gear ratios, have successfully maintained orientation over distances of several hundred meters. But when exposed to real-world conditions, uneven ground, variable friction, slight misalignments, the system begins to fail. Errors accumulate. The figure drifts. The illusion of perfect direction collapses. And yet, the underlying principle remains valid. The mechanism works, just not perfectly, not indefinitely, not without limits. So what then did the ancient texts actually describe? A fully functional navigation device, a symbolic demonstration of mechanical philosophy, or an idealized system, one that worked in principle, but was later remembered as flawless. Some scholars suggest the chariot may have been ceremonial, used in controlled environments where precision could be maintained. Others argue it may have functioned accurately only over short distances, its limitations masked by context. But even these interpretations fail to fully explain the consistency of the records. Across multiple sources, across different centuries, the same core idea appears: a vehicle that preserves direction without sensing it. There is also the possibility that something has been lost, not just the device, but the knowledge required to build it. Ancient technologies are not immune to disappearance. Wars, dynastic collapses, and shifts in cultural priorities can erase entire fields of expertise. If the south-pointing chariot was the product of a specialized mechanical tradition, its techniques may have vanished with the artisans who understood them. What remains are echoes, texts, fragments, and reconstructions that never quite reach the original. So, what do you think? The south-pointing chariot was a real ancient technology, or just an idea ahead of its time shaped by history? Share your thoughts in the comments below. Some artifacts don't just survive the past, they quietly contradict it. Hidden within the valleys of northern Tuscany, a series of ancient stone figures does exactly that. The Benone Stele statues are not massive like pyramids, not mechanically complex like the Antikythera mechanism, and yet they contain a detail so subtle, so technical, that it may quietly rewrite our understanding of prehistoric technology. Because what makes them truly mysterious is not their shape, it is their surface. Near the small settlement of Bagnona within the Lunigiana region, these statues first began to draw attention in the early 20th century, though many had likely been seen for centuries, repurposed in walls, fields, and rural structures without anyone realizing their true origin. It was only during systematic archaeological efforts, especially between the 1940s and 1970s, that researchers began to document them properly, eventually recovering dozens of examples now preserved in places like the Museo del Statue Stele. Through stratigraphic analysis and radiocarbon dating of associated organic materials, their origins were traced back to roughly 3,300 to 2,500 BCE, placing them firmly in the late Neolithic to early Copper Age. At that time, most human societies in Europe were still working with stone tools, with only limited and emerging use of early metallurgy. Precision engineering, as we understand it today, should not have existed here. And yet, something about these statues doesn't fit. At first glance, they seem simple, tall, as flat slabs of sandstone carved into stylized human forms, faces reduced to minimal lines, arms indicated by shallow engraving, sometimes accompanied by depictions of daggers, belts, or ornaments. But the simplicity is deceptive, because the deeper researchers look, the more these statues begin to reveal a hidden layer of complexity, one that is not immediately visible, but physically measurable. Under controlled lighting, under magnification, and eventually under microscopic analysis, a pattern begins to emerge. The surfaces are not rough, not irregular, not unfinished. They are smooth, consistently, deliberately, and in some cases approaching a level of refinement that appears almost unnatural for its time. This is where the anomaly becomes impossible to ignore. Across prehistoric Europe, from the megalithic landscapes of Brittany to the standing stones of the British Isles, stone surfaces typically retain visible tool marks, clear evidence of percussion, chipping, and coarse shaping. Even when shaped into recognizable forms, they rarely show signs of a large-scale surface refinement. In early Egyptian contexts closer to 2600 BCE, smoother finishes begin to appear, but only when copper tools and abrasive compounds are introduced, and even then, such refinement is usually reserved for elite or ceremonial objects. The Banyan stele, however, exist outside this technological framework. They either predate or operate independently of these advancements, yet still achieve a baseline surface uniformity across entire structures. Scientific studies provide measurable evidence of this difference. Microscopic examinations of multiple stele surfaces reveal a consistent reduction in surface roughness when compared to freshly fractured sandstone from the same region. In technical terms, this suggests that the outer layers of the stone were not only shaped, but processed at a microstructural level. The grains appear more compacted, the irregularities reduced, the surface transitions softened. This is not the result of simple carving, it is the result of controlled abrasion. To understand what this means in practice, researchers have turned to experimental archaeology. By attempting to recreate similar surfaces using only tools and materials available during the Neolithic and Copper Age, flint blades, quartzite hammer stones, sand, and water, they have been able to demonstrate that such smoothing is indeed possible. But the cost is time. In controlled conditions, smoothing an area of just 100 square centimeters to a moderately uniform finish can take anywhere from 3 to 6 hours of continuous effort. A typical Banyan stele, however, can exceed 1 meter in height, with an estimated surface area of several thousand square centimeters. When scaled accordingly, the total labor required for a single statue may reach hundreds of hours, potentially even more when accounting for finer finishing stages, and yet these statues are not isolated experiments. Dozens have been discovered across the Lunigiana region, often separated by distance, yet sharing strikingly similar proportions, stylistic features, and, most importantly, surface characteristics. This level of consistency suggests that the smoothing process was not accidental, nor the result of individual experimentation. It was systematic, reproducible, taught, learned, and repeated across generations, which raises a deeper question. What kind of knowledge system existed here that allows such precision to be maintained without leaving behind clear evidence of tools or workshops? Because that is the next layer of the mystery. In most known prehistoric production sites, the act of making leaves traces, debris, broken tools, partially finished objects. But in Lunigiana, such evidence is remarkably scarce. The statues exist, the surfaces are real, the technique is undeniable, but the process is missing. One explanation is that we are witnessing the result of extreme human persistence, labor on a scale that we tend to underestimate. That entire communities may have invested enormous amounts of time into the creation of these objects, driven by cultural, spiritual, or symbolic motivations that justified the effort. But even this raises logistical challenges. Producing dozens of statues, each requiring hundreds of hours, would demand coordination, planning, and continuity. It suggests the presence of specialized artisans, or at least individuals trained in a consistent method, something closer to a craft tradition than random production. Another possibility is that the technique itself was more efficient than we currently understand, that prehistoric artisans may have used specific combinations of materials, certain types of sand, mineral-rich abrasives, or even organic tools such as leather pads or plant fibers to accelerate the smoothing process. These materials would leave little to no trace over thousands of years, making them effectively invisible in the archaeological record. If such techniques existed, they represent a form of practical knowledge that was never written down, never recorded, only passed from one generation to the next and eventually lost. Then there is the durability factor, arguably the most overlooked aspect of all, because the smoothness of these surfaces is not just a visual characteristic, it may also be functional. Many of the stelae, despite thousands of years of exposure to rain, temperature variation, and biological factors, still retain a measurable degree of surface refinement. This has led to the hypothesis that prolonged abrasion may have compacted the outer grain structure of the sandstone, reducing its porosity and making it more resistant to weathering. In modern material science, similar effects are achieved through controlled polishing and compression techniques. If prehistoric artisans discovered a primitive version of this process, through observation, repetition, and experience, it would represent a form of early surface engineering. The context of discovery only deepens the enigma. Many of the statues were not found standing upright in their original locations, but rather reused in later structures or buried in secondary deposits. Some were incorporated into walls, others lay beneath layers of sediment, disconnected from any clear architectural or ritual setting. This makes it difficult to determine their original purpose. Were they markers of territory, memorials to individuals, representations of ancestors or deities, or part of a symbolic system we no longer understand? Whatever their role, the consistency in both form and surface treatment suggests that their creation followed strict conventions, rules that were once known, but are now lost. Do you think these unnaturally smooth surfaces are the result of immense human labour, or the last traces of a lost ancient technique? Share your thoughts in the comments below. At the edge of a quiet lake in northern Greece, within the prehistoric settlement of Dispilio, archaeologists uncovered an object that does not simply belong to the past, it seems to contradict it. Known today as the Dispilio tablet, this small, fragile piece of wood dated through radiocarbon analysis to approximately 5,200 BCE may represent one of the earliest known attempts at recorded information. If this dating holds true, it predates the emergence of the Sumerian writing system by nearly 2 millennia, raising a deeply unsettling possibility that structured symbolic communication, perhaps even writing, existed long before what modern history recognizes as its origin. Yet beyond its age, beyond its enigmatic symbols, it is the manner in which those symbols were carved, the precision, repetition, and control evident in the incisions that has become one of the most difficult aspects of the artifact for modern science to explain. The tablet was discovered in 1993 during systematic excavations led by Professor George Aouamouziadis, who had been studying the lakeside settlement of Dispilio since the early 1990s. The site itself revealed a remarkably advanced Neolithic community, with wooden platforms, organized dwellings, and evidence of coordinated construction over water. Among these findings, the tablet stood out immediately. Measuring roughly 15 centimeters in length and made of wood preserved under anaerobic, waterlogged conditions, it bore a series of engraved symbols arranged in what appeared to be linear sequences. Unlike random markings or decorative scratches, these symbols exhibited repetition, spacing, and structural consistency features that strongly suggest intentional encoding rather than artistic expression. However, it is when researchers began examining the microstructure of these engravings that the true anomaly emerged. The incised lines on the Dispilio tablet are not irregular gouges or hesitant scratches typical of Stone Age carving. Instead, they display a striking degree of uniformity. Many of the lines maintain consistent depth and width across their entire length, indicating a controlled application of force. In several cases, repeated symbols such as angular shapes and parallel strokes are rendered with near-identical proportions, suggesting not only manual skill but also a form of standardization. This level of precision is difficult to reconcile with the known toolkits of Neolithic Europe, which primarily consisted of stone blades, bone implements, and rudimentary metal objects at best. Experimental archaeology offers a partial comparison. When modern researchers attempt to replicate similar carvings using reconstructed Neolithic tools, flint blades or obsidian edges, the results tend to show variability. Even in controlled conditions, maintaining consistent pressure over extended linear incisions proves challenging, often producing uneven grooves, microchipping, and deviations in alignment. Yet the Despilio tablet's engravings lack many of these imperfections. Some lines appear almost guided, as if executed with a steadiness more reminiscent of later metal tools or specialized carving instruments. This discrepancy has led to speculation that either the craftsmen of Despilio possessed tool-making techniques not yet fully understood, or that their level of manual control and training exceeded what is typically attributed to Neolithic societies. The comparison becomes even more striking when placed alongside other early symbolic systems, such as the Vinci symbols found across the Balkans. While the Vinci signs dating to a similar general period do exhibit repeated motifs, they are often inscribed on clay and lack the same degree of linear organization and incision precision. Clay, as a medium, is inherently more forgiving. It allows for correction, smoothing, and reworking before firing. Wood, by contrast, demands accuracy from the first contact of tool to surface. A miscalculation cannot easily be undone. The fact that the Despilio tablet's engravings maintain structural coherence across a wooden substrate implies a deliberate and practiced technique, one that may have required specialized tools or at least a refined understanding of material behavior. Further microscopic analysis has revealed that some incisions penetrate the wood at consistent angles, suggesting that the carving instrument was held at a stable orientation throughout the process. This is particularly difficult to achieve with handheld stone tools, which tend to slip or vary in angle due to their irregular shapes. In addition, the spacing between symbols often follows a pattern that hints at pre-planning. Rather than crowding or drifting across the surface, the symbols are arranged with a sense of alignment, almost as if guidelines, visible or conceptual, were used during carving. Such planning would imply cognitive processes associated with writing systems, layout, sequencing, and spatial organization. Yet perhaps the most perplexing aspect is not the precision itself, but its apparent isolation. There is no clear technological lineage connecting the Despilio tablet to later writing systems. Unlike Mesopotamia, where early pictographs evolved gradually into cuneiform, or Egypt, where hieroglyphs developed alongside monumental architecture and administrative complexity, the Despilio symbols do not appear to have direct descendants. No intermediate forms have been definitively identified. No parallel wooden tablets with similar inscriptions have been preserved at scale. It is as if this technology, this ability to encode and carve structured information with such precision, emerged abruptly and then vanished without leaving a traceable evolutionary path. Compounding the mystery is the fragile nature of the artifact itself. Wood rarely survives for millennia, and the preservation of the Despilio tablet was entirely dependent on the unique conditions of the lakebed low oxygen, constant moisture, and protective sediment. Once removed from this environment, the tablet began to deteriorate rapidly. Despite conservation efforts, portions of the surface and potentially some of the finer details of the engravings have been lost or altered since its discovery. This means that the version we study today may already be an incomplete record, a degraded echo of the original craftsmanship. The possibility that even more precise or intricate features existed before exposure only deepens the enigma. Archaeological campaigns at Despilio have continued to uncover elements of a sophisticated settlement, including tools, pottery, and structural remains that indicate a well-organized community. Radiocarbon dating across multiple samples consistently places the occupation of the site between approximately 6,000 and 5,000 BCE. Yet none of these findings fully account for the technological implications of the tablet's engravings. There is no definitive evidence of advanced metalworking at the time, no specialized carving instruments preserved that could explain the uniformity of the lines. This absence of corroborating technology forces researchers into a difficult position: either accept that Neolithic artisans achieved a level of precision previously unrecognized, or consider that our understanding of their technological capabilities is fundamentally incomplete. In modern terms, the Despelio tablet challenges not just a single assumption, but an entire framework. It questions the timeline of writing, the evolution of tools, and the cognitive development associated with symbolic systems. Most of all, it confronts us with a paradox. How could a society using ostensibly simple tools produce engravings that exhibit such controlled execution, such repeatable geometry, and such deliberate organization? The answer remains elusive. Whether the result of lost techniques, underestimated human skill, or a yet undiscovered technological context, the carving of the Despelio tablet stands as a silent but precise anomaly, one that continues to resist full explanation. What do you think is the Despelio tablet, the earliest form of human writing, or the trace of a lost technology? Share your thoughts in the comments below. Beneath the vast, sun-scorched deserts of Iran lies an engineering system so subtle, so precise, and so enduring that it has been described by modern researchers as an invisible technology, a network that cannot be fully appreciated from the surface, yet silently sustains life across entire regions. Known as the Persian Qanat system, this subterranean hydraulic infrastructure dates back over 2.5 millennia, with some of the earliest examples emerging during the era of the Achaemenid Empire around the 7th century BCE. At first glance, it appears deceptively simple, a gently sloping underground tunnel that channels groundwater from mountainous aquifers to distant arid plains using gravity alone. But upon closer examination, particularly through modern archaeological surveys and hydrological studies, the Qanat reveals a level of precision that challenges conventional assumptions about ancient engineering capabilities. The most striking feature, and arguably the most mysterious, is the extraordinary accuracy of the tunnel gradient. For water to flow consistently across distances that can exceed tens of kilometers, the slope must be maintained within an extremely narrow margin. Studies of well-preserved systems such as the Gonabad Qanat indicate gradients as low as 1 meter per kilometer, or approximately 0.1%. This is not merely a technical detail, it is a constraint that defines the entire system. If the slope were even slightly steeper, the increased velocity of water would erode the tunnel walls, leading to collapse over time. If too shallow, the flow would stagnate, rendering the Qanat ineffective. Modern civil engineers, equipped with laser leveling instruments, GPS, and digital terrain models, still treat such long-distance gradient control as a complex challenge. Yet ancient Persian builders achieved this underground, in complete darkness, without the benefit of direct line-of-sight measurement. Archaeological investigations conducted throughout the 20th century, including detailed mapping by Iranian research teams and UNESCO-supported studies, have revealed the astonishing consistency of these gradients. In Gonabad, for example, the main tunnel extends approximately 70 kilometers and incorporates more than 400 vertical shafts, some descending to depths of over 300 meters. Carbon dating of organic materials found within these shafts, such as wooden supports and sediment layers, places the system's origin around 700 BCE, confirming that it has functioned, with periodic maintenance, for nearly 3,000 years. Satellite imagery and aerial surveys further demonstrate that the surface openings of these shafts form nearly perfect linear alignments, suggesting that the underground tunnel follows a remarkably straight path, despite variations in geology. This raises a fundamental question. How did ancient engineers achieve such precision without modern tools? Comparisons with other ancient water systems only deepen the mystery. The aqueducts of the Roman Empire, often cited as masterpieces of classical engineering, typically maintain gradients between 0.15 and 0.3%, slightly steeper than those of many qanats. However, Roman aqueducts were constructed above ground or along visible contours, allowing engineers to continuously monitor alignment and make adjustments. In contrast, qanat builders worked below the surface, excavating from multiple vertical shafts toward each other, often over distances of several hundred meters between connection points. The probability of maintaining both direction and slope under such conditions, without cumulative error, is extraordinarily low by modern statistical standards. Some hypotheses attempt to explain this phenomenon through the use of simple yet effective tools, plumb lines to ensure vertical accuracy, water-filled trenches to establish level references, and sighting techniques based on the alignment of surface markers. Others emphasize the role of experiential knowledge skills, refined over generations by specialized workers known as muqannis, who may have developed an intuitive understanding of subsurface gradients and soil behavior. Yet even these explanations fall short when confronted with the scale and consistency of the qanat network. Systems spread across different regions of Iran, from Khorasan to Yazd, exhibit similar levels of precision despite variations in terrain, suggesting a standardized methodology that has not been fully documented or recovered. Excavation reports provide tantalizing but incomplete clues. In several qanat sites, archaeologists have uncovered tools such as iron picks, wooden implements, and ceramic vessels, but none that would function as high-precision measuring instruments. There are no surviving technical manuals or inscriptions detailing the construction process. Instead, what remains is the system itself, an enduring physical record of decisions made with a level of accuracy that appears in some respects ahead of its time. Ground-penetrating radar studies conducted in recent decades have shown that many tunnels maintain a consistent cross-sectional profile and orientation, even when passing through layers of varying hardness, from loose sediment to compact rock. This implies not only precise initial planning but also adaptive techniques capable of compensating for geological variation without deviating from the intended gradient. Beyond precision, the qanat system demonstrates an advanced understanding of environmental dynamics. By transporting water entirely underground, it effectively eliminates evaporation losses that can reach up to 50% in open canal systems under desert conditions. This design maintains a stable water temperature and quality, reducing both thermal stress and contamination. Modern engineers recognize these principles in the design of insulated pipelines and subsurface water conveyance systems, yet the qanat achieved similar outcomes millennia earlier, using only locally available materials and labor. The integration of such efficiency with extreme geometric accuracy suggests a holistic approach to engineering, one that combined empirical observation, environmental awareness, and precise execution. The longevity of the system adds another layer of complexity. Many qanats have remained operational for centuries, requiring only periodic clearing of sediment and repair of shafts. This durability indicates that the original builders not only achieved precise alignment, but also selected routes that would remain geologically stable over long periods, avoiding zones prone to collapse or seismic disruption. Modern infrastructure projects often rely on extensive geological surveys and predictive modeling to achieve comparable resilience. Yet there is little evidence that qanat builders had access to such systematic analyses in a formalized sense. In this context, The Persian Qanat system can be seen as a form of invisible engineering, a technology defined not by visible grandeur but by hidden precision. It challenges the linear narrative of technological progress by demonstrating that ancient societies were capable of solving complex problems with a level of accuracy that remains difficult to replicate without advanced tools. The Qanat is not merely an irrigation method. It is a manifestation of a sophisticated knowledge system, one that has left behind few written traces but an abundance of physical evidence. As modern researchers continue to study these systems using advanced imaging techniques and hydrological modeling, the core mystery persists. How did ancient Persian engineers, working with what appear to be simple tools and limited theoretical frameworks, achieve such consistent and precise underground gradients over vast distances? Was it the result of lost techniques, an accumulation of empirical knowledge beyond our current understanding, or something else entirely? The tunnels remain, quietly carrying water beneath the desert, offering no direct answers, only a silent testament to a level of precision that still defies full explanation. What do you think allowed ancient Persian engineers to achieve such near-perfect precision, lost knowledge, generations of accumulated experience, or a technology we still don't fully understand? Share your thoughts in the comments below. At the ancient lakeside settlement of Starkar, dating back approximately 9,000 years to the early Mesolithic period, archaeologists uncovered a collection of objects that continue to unsettle conventional understanding of prehistoric technology. A series of modified red deer skulls, carefully transformed into what are now called headdresses. First excavated in 1948 by Graham Clark, and later revisited through major excavations between 2004 and 2015, led by Nikki Milner and her team. More than 21 of these headdresses have been documented, preserved in extraordinary detail by the oxygen-poor peat of what was once a shallow lake edge. While their symbolic or ritual purpose remains debated, it is the method of their construction, particularly the astonishing precision in modifying dense deer skulls, that has emerged as one of the most perplexing technological questions associated with the site. Far from crude adaptations, these objects display a level of workmanship that appears fundamentally at odds with the limitations of Mesolithic stone tools. Each headdress began as the upper cranium of a red deer, complete with antlers, one of the densest and most structurally complex biological materials available to hunter-gatherers of the time. The process of transformation required the deliberate removal of the lower jaw and, more significantly, the controlled cutting away of the cranial base to create a hollow cavity capable of fitting over a human head. This is not a trivial task. Experimental archaeology demonstrates that working with fresh bone using flint tools typically results in irregular fractures, unpredictable splitting, and jagged edges due to the heterogeneous composition of bone tissue. Yet the Starkar specimens frequently show cut lines that are remarkably consistent, following clean arcs or planes rather than chaotic break patterns. Microscopic analysis of these surfaces has revealed parallel striations indicative of repeated, directional tool movement, suggesting a methodical scoring technique rather than brute force hacking. In some cases, the edges appear subtly smoothed, as if additional finishing processes were applied after the initial cut, further complicating attempts to replicate the results using known Mesolithic methods. The precision does not end with the removal of bone. Around the perimeter of several headdresses, archaeologists have identified carefully placed perforations, often spaced with notable regularity. These holes, likely used to attach bindings made of sinew or plant fibers, required the controlled penetration of thick cranial bone without causing structural failure. Flint tools or points, the most plausible tools available at the time, are capable of piercing bone, but maintaining consistent spacing and avoiding cracks across multiple perforations demands a level of planning and dexterity rarely attributed to early Mesolithic craftsmanship. Measurements taken from different specimens reveal patterns in hole placement that suggest not only functional intent, but also an implicit design, logic balancing, stability, weight distribution, and wearability. Such consistency across more than 21 examples implies that these were not isolated experiments, but products of a shared and possibly standardized technological tradition. To understand the scale of this achievement, it is useful to compare the star-car headdresses with other known bone-working traditions. At later Neolithic and even Bronze Age sites, where metal tools were available, bone modification often exhibits similar levels of precision, but these technologies emerged thousands of years after star-car. In earlier or contemporary Mesolithic contexts across Europe, modified animal remains are typically far less refined, with evidence of opportunistic shaping rather than controlled engineering. The star-car artifacts, by contrast, suggest a degree of foresight and repeatability more commonly associated with much later periods. Radiocarbon dating places the main phase of activity at the site between approximately 9,000 and 8,500 BCE, and yet within this time frame, the headdresses display a remarkable uniformity in both form and technique. This raises a critical question: how did a community operating without metal tools, without formalized workshops, and without written knowledge systems achieve such reproducible precision? One hypothesis proposes that the craftspeople of star-car employed techniques to alter the physical properties of bone prior to cutting. Ethnographic parallels and experimental studies indicate that soaking bone in water, subjecting it to heat, or allowing partial microbial decomposition can significantly reduce its hardness and increase its workability. If such methods were used, they could explain the smoother cuts and reduced fracturing observed in the archaeological specimens. However, this remains speculative. No direct chemical or structural evidence has conclusively demonstrated that such pre-treatment occurred at star-car, and even if it did, the exact parameters, duration, temperature, environmental conditions remain unknown. Without this knowledge, modern attempts to replicate the headdresses have achieved only partial success, often producing results that fall short of the original artifacts in terms of edge, regularity, and structural integrity. Further complicating the picture is the evidence for ergonomic adaptation. The interior of several headdresses shows signs of deliberate shaping to accommodate the contours of the human skull. In some examples, the nasal bones have been modified or removed, potentially to improve visibility or reduce weight. The distribution of perforations suggests an understanding of how to secure the object firmly, while minimizing discomfort during movement. These are not random adjustments but targeted modifications that indicate a sophisticated awareness of the interaction between material and body. When combined with the precision of the cutting and drilling, they point toward a level of design thinking that challenges simplistic models of Mesolithic life as purely reactive or survival-driven. The broader archaeological context reinforces the significance of these findings. The excavations conducted in the early 21st century employed high-resolution recording methods, including three-dimensional mapping and microstratigraphic analysis, revealing that the headdresses were deposited in specific zones within the site, often associated with other carefully placed organic artifacts such as antler frontlets, worked wood, and plant remains. This patterning suggests intentional deposition, possibly linked to ritual activities. Yet even if the headdresses served symbolic or ceremonial functions, their production required a technological investment that goes beyond what is typically expected for purely ritual objects. The time, skill, and knowledge required to produce even a single headdress would have been substantial, implying that their makers possessed not only technical expertise, but also the social framework to support and transmit that expertise across generations. In total, the star-car headdresses force a reconsideration of what Mesolithic technology was capable of achieving. The evidence over 21 carefully modified skulls, consistent in design, exhibiting controlled cuts, evenly spaced perforations, and ergonomic shaping does not align easily with the idea of crude, trial-and-error craftsmanship. Instead, it suggests a system of knowledge, possibly including material pre-treatment, sequential tool use, and design planning, that has left no direct trace beyond the artifacts themselves. Unlike stone tools, which can be studied in terms of manufacturing sequences and wear patterns, the processes behind these organic objects remain largely invisible, preserved only in their final form. And it is precisely this invisibility, the gap between what we can observe and what we can explain, that keeps the star-car headdresses at the center of one of archaeology's most intriguing technological mysteries. So what do you think? Were these headdresses the result of lost advanced techniques, or are we underestimating Mesolithic skill? Share your thoughts in the comments below. Thanks for watching, and next video. Long before the first cities rose in the fertile lands of Mesopotamia, before monumental architecture or written language defined what we call civilization, a settlement known as Chogamish was already demonstrating something that continues to unsettle modern archaeology. A fully operational irrigation system that appears, almost inexplicably, far too early and far too complete. Excavated in multiple campaigns between 1961 and 1978 by Pinhas de Lugas and Helene Cantor of the Oriental Institute of the University of Chicago, Chogamish revealed occupational layers dating back to approximately 6,800 BCE, placing it nearly 9,000 years before the present. Within these layers, archaeologists uncovered evidence of artificial canals, structured water channels, and integrated drainage features, components that, taken together, suggest not an experimental or primitive attempt at irrigation, but a system that was already coherent, organized, and remarkably efficient from its earliest known phase. What makes this discovery particularly mysterious is not merely the presence of irrigation, but the absence of any visible developmental trajectory leading up to it. In most models of technological evolution, systems as complex as controlled irrigation emerge gradually, through incremental improvements over generations, beginning with simple diversion ditches, evolving into more stable channels, and eventually developing into large-scale coordinated networks. Yet at Chogamish, the archaeological record appears to skip these intermediate stages entirely. The canals identified in the earliest layers already display features of controlled gradient flow, indicating that water was directed with precision rather than allowed to spread unpredictably. Some channels seem to have been constructed with slopes subtle enough to maintain steady flow without causing erosion, a balance that even modern hydraulic engineering considers a significant challenge. The implication is striking. Whoever designed these systems possessed an empirical understanding of hydrodynamics that, according to conventional timelines, should not have existed so early. To fully grasp the anomaly, it is essential to compare Chogamish with other contemporary and later civilizations. In early Neolithic communities across Anatolia and the Levant, dating to roughly the same period, agriculture was predominantly rain-fed or dependent on natural floodplains, with little evidence of engineered water control beyond rudimentary modifications. Even in southern Mesopotamia, where irrigation would later become the backbone of urban development, large-scale canal systems do not become clearly visible until the Ubaid period, around 5000 BCE, over 1,000 years after the earliest phases of Chogamish. Similarly, in ancient Egypt, Early agricultural practices relied heavily on the cyclical flooding of the Nile, with systematic irrigation infrastructure emerging gradually and closely tied to centralized state authority. The contrast is difficult to ignore. While other regions were still adapting to water, Choggamish appears to have been actively controlling it. The environmental context only deepens the puzzle. Situated in the Susiana Plain near the Des River, the region is characterized by fluctuating water levels, seasonal droughts, and unpredictable flooding patterns. Modern hydrological assessments suggest that sustaining agriculture in such an environment without sophisticated management would be extremely difficult. And yet, the inhabitants of Choggamish not only survived but thrived, building a system capable of distributing water across cultivated fields while simultaneously protecting the settlement from excess runoff. Excavation data indicates that some water channels were integrated into residential zones, possibly serving dual purposes, irrigation and drainage, suggesting a level of planning that blurs the line between agricultural engineering and early urban design. Another layer of complexity emerges when considering the scale of organization required to construct and maintain such a system. Irrigation infrastructure is not a one-time achievement. It demands continuous upkeep, coordination of labor, and regulation of water access. This implies the existence of a social framework capable of managing shared resources, enforcing rules, and allocating labor, a proto-administrative system that predates what we traditionally recognize as formal governance. In many later civilizations, such as those of Mesopotamia and the Indus Valley, large-scale water management is closely associated with the rise of centralized authority. But at Choggamish, this level of coordination appears to exist without clear evidence of hierarchical political structures, raising the possibility that complex social organization may have originated, at least in part, from the necessity of controlling water rather than from urbanization itself. Perhaps the most perplexing aspect, however, is what is missing. Despite decades of excavation and analysis, archaeologists have found no definitive tools specifically associated with canal construction. No written instructions or symbolic representations explaining the system, and no preserved models indicating how these early engineers conceptualized their work. What remains are the traces, the physical imprints of canals carved into the earth, silent evidence of a technological capability that appears to have emerged fully formed. Modern experimental reconstructions have attempted to replicate similar systems using only Neolithic-era tools and methods. Yet even these efforts often rely on assumptions about knowledge transfer and long-term observation that are difficult to verify. This absence of transitional evidence has led some researchers to question whether the apparent suddenness of the system's emergence reflects a genuine leap in knowledge or simply gaps in the archaeological record. It is possible that earlier, more primitive irrigation experiments existed but have not yet been discovered, eroded by time or buried beneath unexcavated layers. Yet until such evidence is found, Choggamish stands as an anomaly, a point in history where technological sophistication seems to outpace its own evolutionary context. When viewed through a broader lens, the irrigation system of Choggamish challenges one of the most deeply ingrained assumptions about human progress. That complexity emerges slowly, step by step, in a predictable sequence. Instead, it hints at a different pattern, one in which knowledge can appear, fully realized, under conditions we do not yet fully understand, only to be partially lost, rediscovered, or reinterpreted by later civilizations. The canals of Choggamish, with their carefully measured slopes and integrated design, are more than agricultural tools. They are a message from a distant past, suggesting that nearly 9,000 years ago, human beings were capable of engineering feats that still defy complete explanation. And so the central mystery remains unresolved. How did a community so ancient, lacking metal, writing, or formal science, create a water management system that appears not as a beginning but as a culmination? Was it the result of generations of forgotten experimentation, a unique convergence of environmental necessity and human ingenuity, or evidence of a lost chapter in technological history that has yet to be uncovered? What do you think was the Chogga-Mish irrigation system a natural evolution of human ingenuity, or evidence of a lost and forgotten technology? Share your thoughts in the comments below. Discovered in 2021 during a rescue excavation near the shores of Tyrifjord in Norway, the Svingerud runestone has rapidly redefined what archaeologists thought they understood about the earliest phases of runic writing, and more disturbingly, about the technological capabilities of Iron Age societies in Northern Europe. Unearthed from a cremation burial context containing burnt bones and charcoal fragments, the stone was subjected to radiocarbon dating through associated organic remains, producing a calibrated date range between approximately 1 and 250 CE. This alone was enough to send shockwaves through the academic community, as it places the inscription centuries earlier than many previously confirmed examples of the Elder Futhark system. Excavations led by teams affiliated with the University of Oslo throughout 2021, 2022, and follow-up analyses in 2023 revealed not only the primary inscribed slab, but also additional fragmented stones bearing partial markings, suggesting that the site may have been reused or that multiple inscription events occurred over time. Yet despite the significance of its early date and ambiguous linguistic content, the most unsettling aspect of the Svingerud runestone lies in the physical characteristics of its engravings features that appear to exceed the expected limitations of Iron Age carving technology. At first glance, the runes appear deceptively simple, linear incisions arranged in sequences that resemble early forms of known characters. But under magnification, particularly through high-resolution microscopy and three-dimensional surface scanning conducted in laboratory conditions, the grooves reveal a level of precision that is extraordinarily difficult to reconcile with the tools believed to have been available at the time. Measurements taken from several rune segments indicate that the incisions maintain a width often below 1 millimeter, with depth variations typically constrained within a narrow band of approximately 5 to 10% across individual strokes. This degree of consistency is highly unusual. By comparison, experimental archaeology efforts attempting to reproduce similar engravings using reconstructed Iron Age iron chisels, tools forged with carbon contents and hardness levels consistent with early Scandinavian metallurgy, have yielded grooves with depth variations ranging from 25 to 40%, even under controlled conditions and with skilled modern practitioners. The discrepancy suggests that either the ancient engraver possessed an exceptional level of manual control far beyond what is typically assumed, or that alternative techniques were employed techniques for which there is currently no direct archaeological evidence. The geometry of the incisions further complicates the picture. Several rune intersections form clean, sharply defined angles that imply deliberate planning and controlled execution, rather than the cumulative effect of repeated, imprecise strikes. In many cases, the termination points of lines are crisp rather than tapered, indicating that the tool was lifted or redirected with remarkable accuracy. This contrasts sharply with contemporaneous inscriptions found on bone, wood, and even other stone artifacts from the same general period, which often display irregular endpoints, microchipping, and visible hesitation marks where the tool slipped or lost alignment. Even later runestones from the 4th to 6th centuries produced during a time when ironworking techniques had improved, frequently exhibit broader, less uniform grooves and more evident signs of manual correction. The Sphingurud engravings, by contrast, lack these imperfections to a striking degree. Material analysis of the stone itself introduces yet another layer of difficulty. The slab appears to consist of a relatively hard metamorphic rock, requiring sustained pressure and a sufficiently sharp edge to incise effectively. Under typical conditions, carving such material with early iron tools would produce secondary damage in the form of flaking or microfractures along the groove edges. However, microscopic inspection of the Sphingurud runestone reveals minimal collateral disruption to the surrounding surface. The groove walls are comparatively smooth, and in some sections they exhibit a subtle polish-like quality, as though the surface had been abraded or refined after the initial incision. This has led some researchers to propose that the carving process may have involved a combination of techniques, perhaps initial pecking, followed by grinding with fine abrasive materials such as sand or quartz particles. Yet even this hypothesis raises further questions, as controlled abrasion of this kind would require not only time and skill, but also a level of process standardization that is not well documented for the period. The absence of a clear technological progression leading up to such precision remains one of the most troubling aspects of the find. In other early writing traditions, whether in Mesopotamia, Egypt, or even later Germanic contexts, there is typically a visible evolution from crude, inconsistent markings to more refined and standardized forms. Early attempts are marked by irregular spacing, uneven depth, and frequent errors, gradually giving way to greater uniformity as techniques improve. In the case of the Sphingurud runestone, however, this developmental trajectory appears to be missing. The engravings do not look like experimental first attempts. Rather, they give the impression of a method already understood and practiced. Yet no earlier Scandinavian artifacts displaying comparable levels of precision have been definitively identified. This discontinuity suggests either a gap in the archaeological record where intermediate examples have not survived or have yet to be discovered, or the existence of a localized tradition of craftsmanship that developed independently and left little trace beyond this site. Excavation reports from 2021 through 2023 also note that the stone was not an isolated object but part of a more complex funerary environment. The burial site appears to have been reused over time, with layers of deposits indicating multiple phases of ritual activity. Some fragments of inscribed stone were found in secondary positions, possibly displaced or intentionally broken and redistributed. This raises the possibility that the runestone itself may have been handled, repositioned, or even reinterpreted by later generations, complicating efforts to establish a precise chronological relationship between the carving and the burial context. Nevertheless, the consistency of the engraving style across different fragments suggests a shared technique or origin, reinforcing the idea that the precision observed is not accidental but systematic. When placed in a broader comparative framework, the Sphingurud runestone stands out not only within Scandinavia, but across early inscriptional traditions more generally. While fine engraving is not unknown in antiquity, examples from later Roman inscriptions or carefully executed Greek epigraphy demonstrate high levels of craftsmanship. Such precision is typically associated with well-developed toolkits, standardized chisels, and often professional stoneworking traditions supported by complex societies. In contrast, early Iron Age Scandinavia is not generally characterized by this level of technological specialization in stone carving. The apparent mismatch between expected capability and observed result is precisely what makes the Sphingurud engravings so difficult to explain within existing models. In the end, the Sphingurud runestone reveals a striking contradiction: an unexpectedly early origin, a ritual burial context, an engraving precision that challenges what Iron Age tools should have achieved. Whether this reflects lost techniques, underestimated craftsmanship, or exceptional skill remains unknown. What is certain is that it does not fit the known path of technological development, leaving us with a past that still resists full explanation. So, what do you think, was this level of precision truly achievable with Iron Age tools, or are we missing a piece of ancient technology? Share your thoughts in the comments below. Tel Saf lies in the Jordan Valley, a place that today appears dry, exposed, and unremarkable. But beneath its surface, archaeologists uncovered something that should not exist this early in human history: a system of grain silos so technically refined that it forces a reconsideration of what Neolithic societies were capable of. Dating to roughly 5,200 to 4,600 BCE, Tel Saf belongs to a period long before the rise of urban civilizations in Mesopotamia, before writing, before large-scale metallurgy. And yet, the excavation campaigns led by researchers from institutions such as the University of Haifa and the Hebrew University of Jerusalem revealed storage installations that appear not only organized and large-scale, but engineered with a level of environmental control that seems far ahead of its time. What makes the Tel Saf grain silos so perplexing is not simply their size, though that alone is striking. Individual silos, constructed primarily from mud brick, are estimated to have held between 20 and 30 tons of grain, predominantly wheat and barley. This capacity far exceeds the needs of a single household and implies a level of surplus production, planning, and centralized storage that would not become common until thousands of years later in early state societies. At sites like early Jericho or Çatalhöyük, storage was typically decentralized small bins, often integrated into domestic architecture, holding modest quantities intended for short-term use. By contrast, Tel Saf's silos appear to have been purpose-built, communal and standardized in both form and function. But even more astonishing than their scale is the apparent sophistication of their construction, particularly in how they managed environmental conditions critical for long-term grain preservation. Modern grain storage requires careful control of moisture, temperature, and oxygen levels to prevent spoilage, fungal growth, and insect infestation. Today, industrial silos rely on engineered ventilation systems, chemical treatments, and precise monitoring technologies. Yet at Tel Saf, long before any formal scientific understanding of microbiology or chemistry, the builders seem to have achieved a functional equivalent through architectural design alone. Excavations have shown that many of the silos were built on slightly elevated platforms, sometimes with stone foundations beneath the mud brick walls. This elevation would have reduced direct contact with ground moisture, a major factor in grain spoilage. In addition, the walls themselves were unusually thick, sometimes exceeding 0.5 meter, creating a form of thermal mass that would buffer internal temperatures against the extreme fluctuations typical of the Jordan Valley climate, where daytime heat can be intense and nighttime temperatures drop sharply. Further analysis of the internal surfaces of these silos revealed traces of plastering, possibly made from lime or clay mixtures. Such coatings would have served multiple functions: sealing micro-cracks in the mud brick, reducing air infiltration, and potentially creating a barrier against insects and microorganisms. In some cases, the plaster appears to have been applied in multiple layers, suggesting maintenance and perhaps even a developed understanding of how to prolong the functional lifespan of the structure. This is particularly striking when compared to other contemporary sites, where mud brick constructions were often more rudimentary and less systematically treated. At Tel Saf, the evidence suggests intentional design choices aimed at controlling the internal environment of the silo a level of foresight that borders on proto-engineering. One of the most debated aspects among archaeologists is the possibility of passive ventilation systems. While no mechanical vents have been found in the modern sense, the geometry and placement of certain openings, combined with the cylindrical shape of the silos, may have allowed for subtle air circulation driven by temperature gradients. Warm air rising within the structure could escape through small gaps or openings, drawing in cooler air from below and creating a slow, continuous exchange. Such a system, while simple, could significantly reduce humidity and inhibit the growth of mold. If this interpretation is correct, it would mean that the builders of Tel Saf were not only aware of the dangers of stagnant air, but had developed architectural solutions to mitigate them without any formal theoretical framework. The precision with which these silos were constructed adds another layer to the mystery. Measurements taken during excavation indicate that many of the structures are remarkably consistent in diameter and volume, suggesting some form of standardization. This is difficult to explain in a context where no known system of measurement or geometric tools existed in a formalized way. Yet the circularity of the silos is often close to ideal, and their capacities appear calibrated, perhaps to facilitate accounting, distribution, or trade. Such regularity implies not only skilled craftsmanship, but also a conceptual understanding of space and volume that challenges assumptions about Neolithic cognitive and technical abilities. The question then arises, how effective were these systems in practice? Botanical analyses of grain residues found at the site suggest that storage was indeed successful over extended periods. There is evidence that grain was kept in conditions that limited spoilage, supporting the idea that these silos were not merely symbolic or experimental, but fully functional components of a broader economic system. This aligns with the discovery of imported materials at Tel Saf obsidian from Anatolia, shells from the Mediterranean indicating participation in long-distance exchange networks. In such a context, the ability to store large quantities of grain reliably would have conferred significant economic and social power. Comparisons with later civilizations only deepen the enigma. In Mesopotamia, large-scale storage facilities become prominent during the Uruk period, around 3500 BCE, nearly 2 millennia after Tel Saf. These later silos, often associated with temples or administrative centers, are part of complex bureaucratic systems involving written records and centralized control. Yet Tel Saf seems to anticipate many of these features without the accompanying institutional framework. There is no evidence of writing, no monumental architecture, no clear administrative buildings, only the silos themselves, standing as silent indicators of a system that should not yet exist. Multiple excavation seasons, particularly those conducted in the early 2010s, have expanded the dataset, revealing not just isolated structures, but an entire landscape organized around storage. The repetition of similar silo designs across different areas of the site reinforces the idea of shared knowledge and possibly coordinated construction efforts. This was not a one-off innovation, but a sustained practice, maintained and replicated over generations. And yet, for reasons that remain unclear, this technological approach did not spread widely, nor did it leave a clear legacy in subsequent cultures. This discontinuity is perhaps the most unsettling aspect of Tel Saf. If such advanced environmental control in grain storage was achieved so early, why do we not see a continuous trajectory leading to later developments? Was this knowledge lost, forgotten, or simply not transmitted? Or does it suggest that our current archaeological record is incomplete? That there were other sites, other communities, equally advanced in their own ways, that have yet to be discovered or have not survived the passage of time? In the end, the grain silos of Tel Saf stand as a paradox. They are at once simple, constructed from mud brick, shaped by hand, and profoundly sophisticated in their function. They embody a form of practical knowledge that operates just below the threshold of what we typically recognize as technology, yet achieves results comparable to much later, more explicitly engineered systems. They challenge the linear narrative of human progress, suggesting instead that complexity can emerge early, unexpectedly, and perhaps even disappear without a trace. And in that sense, Tel Saf is not just an archaeological site, it is a reminder that the past may have been far more advanced in ways we are only beginning to understand than we have ever imagined. So here's the real question. If a site like Tel Saf could achieve this level of precision and environmental control 7,000 years ago, are we underestimating ancient human technology? Or are we missing entire chapters of history? Tell me what you think in the comments below. A structure built from mud should not survive 5,000 years, and yet rising silently from the plains near Malatya, the ancient mound of Arslan Tepe tells a story that challenges everything we think we know about early human civilization. Because this is not just a ruin, but a system, a machine of power, control, and engineering that appears far earlier than it should in the human timeline, where materials considered fragile behave as if engineered for permanence, and where the very existence of such durability forces us to question whether ancient knowledge has been underestimated or even lost entirely. Arslan Tepe sits at a strategic crossroads between Anatolia and Mesopotamia, a region often considered a bridge between emerging civilizations and dating back to the late Chalcolithic period. Around 3,500 to 3,000 BCE, the site predates or exists alongside early urban centers like Uruk. Yet unlike Uruk, which shows a gradual transition from village life to urban complexity, Arslan Tepe presents something far more unsettling, a fully organized administrative and architectural system appearing almost all at once without the expected evolutionary steps, suggesting either a missing developmental phase or a sudden leap in social and technical capability that current archaeological models struggle to explain. Systematic excavations began in the 1960s, led by Italian archaeologists from Sapienza University of Rome, most prominently Marcella Frangipane, and what they uncovered was not a simple settlement but a palace complex, one of the earliest ever discovered, where layer-by-layer excavation campaigns revealed monumental mud brick walls, long corridors with controlled access, storage rooms sealed with administrative clay tokens, and ceremonial spaces with painted decoration, each archaeological season adding new data points such as carbon-dated organic remains, confirming occupation phases, stratigraphic layers indicating long-term continuity, and architectural expansions suggesting planned development, while simultaneously deepening the mystery surrounding how such an advanced and organized system could emerge so early with so little evidence of transitional stages. One of the most shocking discoveries came from a cache dated to around 3,300 BCE, a group of arsenical bronze swords among the oldest metal weapons ever found. And these were not crude tools but engineered objects made of copper, alloyed with arsenic for increased hardness, in some cases containing up to several percent arsenic to improve mechanical strength, with certain blades decorated with silver inlays and exhibiting uniformity in length, balance, and form, which strongly suggests controlled metallurgical processes, while alongside these weapons, archaeologists uncovered hundreds of clay ceilings used to control goods and storage, indicating a centralized administrative system capable of tracking resources, yet in Sumer such systems developed in parallel with writing, whereas at Arslan Tepe they appear before writing is fully formed, raising the unresolved question of how information was encoded, managed, and enforced without a fully developed written language. The palace itself reveals a level of planning that should not yet exist. With orthogonal corridors designed for controlled movement, hierarchical room arrangements separating administrative and ceremonial functions, and restricted access points suggesting authority, surveillance, and social stratification, transforming the structure into something far beyond a settlement and instead into a physical embodiment of governance, where architecture itself regulates behavior. And when compared to early Mesopotamian settlements where structures evolved organically through incremental expansion, Arslan Tepe appears to have been designed from the outset as a centralized and intentional system of power, implying the existence of planning concepts and spatial logic that are rarely documented at such an early stage in human history. But the deepest mystery is not what was built, it is how it has survived, because the palace is constructed almost entirely from mud brick, a material typically composed of clay, water, and organic temper, and known to degrade rapidly under environmental stress. And yet the walls of Arslan Tepe still stand several meters high after more than 5,000 years, with some preserved sections maintaining structural coherence and even retaining plaster coatings and painted geometric patterns in red and black pigments, a level of preservation that is statistically abnormal when compared to contemporaneous sites across Mesopotamia, where mud brick architecture often erodes within a few centuries, collapsing and requiring continuous rebuilding. While at Arslan Tepe, the survival rate suggests a level of material optimization and environmental adaptation that goes far beyond what is typically expected from prehistoric construction techniques. Laboratory studies of the bricks reveal standardized dimensions, often around 40 by 40 by 10 centimeters, indicating controlled production, while compositional analysis shows carefully balanced mixtures of clay and silt combined with finely processed vegetal fibers distributed uniformly throughout the material. A microscopic examination reveals that these fibers may have been intentionally oriented to improve tensile strength and reduce cracking, while density measurements suggest controlled compaction and drying processes, possibly involving staged curing cycles to prevent internal stress fractures. And when compared to experimentally recreated mud bricks using similar materials, the ancient samples demonstrate significantly higher cohesion and resistance to weathering, suggesting that Arslan Tepe builders possessed empirical knowledge of material behavior that has not been fully reconstructed. Further evidence suggests that Arslan Tepe builders understood environmental stress in ways that modern researchers still struggle to replicate, as thin plaster coatings, sometimes less than a centimeter thick, may have functioned as protective barriers against moisture infiltration, while surface treatments such as burnishing or repeated layering could have reduced water absorption rates, and architectural features including drainage channels, elevated platforms, and controlled gradients indicate a deliberate approach to water management, minimizing erosion and capillary rise. Yet modern experimental archaeology has shown that even when replicating these techniques with local materials, reconstructed bricks often degrade within decades, while the original structures have endured for millennia, suggesting that a critical variable, whether chemical composition, curing method, or environmental interaction, remains unknown and possibly represents a lost technological process. When placed side by side with other early sites, Uruk demonstrates gradual urban evolution over multiple phases. Mesopotamian mud brick architecture requires continuous rebuilding due to rapid degradation, and other Anatolian settlements of similar age lack comparable structural preservation. Yet Arslan Tepe deviates from all of these patterns, as it is not the earliest known site, yet exhibits a level of durability and organizational complexity that appears disproportionate to its chronological position, reinforcing the idea that it represents an anomaly in the expected trajectory of early human development. Arslan Tepe suggests that technological progress in ancient times may not have been linear, but instead capable of rapid leaps within specific societies, where advanced metallurgy, centralized administration, complex architecture, and highly optimized material engineering appeared earlier than expected, and in some cases in forms that modern experiments still struggle to replicate, raising the possibility that ancient innovation was not only more advanced than we assume, but also more uneven and potentially lost over time. In your opinion, is Arslan Tepe evidence of a lost technology, or are we simply underestimating the capabilities of ancient humans? Share your thoughts in the comments below. It doesn't begin with a civilization, or a monument, or even a legend. It begins with a mistake. In the early 20th century, a large broken stone was unearthed in the Brittany region of France, catalogued and then quietly forgotten. There was nothing outwardly spectacular about it. No gold, no inscriptions, no obvious symbolism. Just a slab, heavy, fractured, and seemingly insignificant. For over a century it remained in storage, dismissed as another relic of a distant and poorly understood past. But what if that dismissal was wrong? What if that stone was not a relic, but a message? Today we know it as the Saint-Belec slab, and it may be one of the most disruptive archaeological discoveries ever made in Europe. Measuring roughly 2.2 meters in length and weighing over 1 ton, this slab was originally discovered in 1900, then re-examined between 2014 and 2021 by researchers, including teams associated with the French National Institute for Preventive Archaeological Research. What began as a routine reanalysis quickly evolved into something far more profound. Because when the slab was subjected to high-resolution three-dimensional scanning, something unexpected emerged. The chaotic lines on its surface were not random. They were structured, deliberate, and most disturbingly, they matched the real world. When scientists overlaid the slab's engravings onto modern digital elevation models of the Odette River Valley, the results were staggering. The carved lines aligned with the river's course and its tributaries with an estimated accuracy of up to 80%, not 10%, a not symbolic resemblance, but a measurable, repeatable correlation. River bends, valley contours, and relative distances between key features showed consistent alignment across multiple segments of the stone. In controlled spatial analyses, segments of the slab were compared against real terrain using GIS-style correlation methods, revealing repeated pattern matches that would be statistically unlikely if the engravings were purely decorative. In some areas, distortions could be explained by erosion, breakage, or deliberate abstraction, but the underlying structure remained coherent. This was not coincidence. This was representation, intentional, measured, and encoded. To grasp the magnitude of this, we need to step back into the Bronze Age, approximately 1900 to 1600 BCE. At that time, there were no known coordinate systems, no triangulation methods, no aerial perspective, and no mathematical frameworks capable of projecting three-dimensional landscapes onto two-dimensional surfaces. Even much later, early maps created by thinkers like Anaximander in the 6th century BCE were symbolic, often circular, and lacked measurable accuracy. It was not until the work of Claudius Ptolemy in the 2nd century CE that coordinate-based cartography began to approach something resembling scientific mapping, and even then distortions were significant due to incomplete data. And yet, more than 1,000 years before Ptolemy, someone, or some group, etched a landscape into stone and achieved a level of accuracy that modern analysis can still recognize. The Saint-Belec slab does not simply depict lines, it encodes territory. The engraved network appears to correspond to a real geographic region spanning roughly 30 by 20 kilometers in the Odette Valley. The density and distribution of carvings suggest not random artistry, but structured information, possibly rivers, boundaries, routes, and zones of control. Some researchers propose that it may represent one of the earliest known examples of a territorial map, perhaps used by a ruling elite to define land ownership or political influence. If that interpretation is correct, then this is not just a technical achievement, it is evidence of administrative complexity. A society capable of mapping land this precisely is not primitive. It is organized, strategic, and aware of spatial control. But the question remains, how? Without aerial views, mapping must be done from the ground. Then one theory suggests systematic traversal. Individuals walking the landscape, memorizing distances and translating them into proportional relationships. But to maintain consistency across a 2-meter stone surface requires more than memory. It requires a system. Perhaps they used pacing methods, where distance is measured in steps. Perhaps they aligned sightlines between landmarks, using elevated positions to triangulate direction. Some have even speculated about the use of primitive surveying tools, ropes, stakes, or shadow-based measurements. Yet no direct archaeological evidence confirms the existence of such instruments in this context. Equally mysterious is the slab's 3-dimensional structure. It is not flat. Subtle depressions and raised areas correspond to valleys and elevations, suggesting an attempt to encode topography, not just layout. This transforms the slab into something closer to a relief map. In modern cartography, this would require elevation data and contour mapping. In the Bronze Age, it implies an extraordinary cognitive ability, the translation of real-world terrain into a scaled physical abstraction that preserves both shape and height. The story becomes even more complex when we consider how the slab was found. It was not preserved as an object of importance. It had been broken, deliberately, and reused as part of a burial structure. This suggests that by the time it was interred, its original function had already been lost, rejected, or erased. Was it destroyed during a shift in power? Was it associated with a leader whose authority was overthrown? Or was it considered dangerous knowledge, something that needed to be hidden? In archaeology, intentional destruction often signals cultural transition, conflict, or symbolic rejection. The fate of the slab hints at a story we do not yet fully understand. Surrounding archaeological evidence offers partial clues. Excavations in Brittany have revealed fortified settlements, long-distance trade connections, and signs of hierarchical societies during the Late Bronze Age. These were not isolated tribes. They were organized communities capable of coordinated construction, economic exchange, and territorial management. In such a context, a map is not a curiosity. It is a tool of power, a way to define borders, allocate resources, and maintain control. And yet, despite all this, the St. Belec slab stands alone. No other artifact of similar scale, purpose, or precision has been discovered from the same period in Europe. There are no earlier prototypes showing gradual development, no later examples that build upon its design. It appears suddenly, fully realized, and then disappears from the archaeological record. This absence of continuity challenges one of the most fundamental assumptions about human progress, that knowledge evolves step by step, building upon previous discoveries. But what if that assumption is wrong? What if knowledge can emerge in isolated moments, fully formed, context-specific, and then vanish without leaving a trace? Experimental archaeology has attempted to replicate the slab using Bronze Age tools. Stone hammers, wooden mallets, early bronze chisels, all have been tested. The conclusion is clear. It is possible to carve such a surface, but not easily. Achieving the same consistency in line depth, curvature, and spatial alignment across a slab of this size requires not only skill, but planning, repetition, precision. In other words, it requires intent. and intent implies understanding. Do you think this slab is truly just a map or evidence of an ancient knowledge system we still don't fully understand? Share your thoughts in the comments below.